n many elements. Yes, this is the terminology they are using, and we are using that. And that's a joint work with Valentin, still going, because there are things we want to do and we did not do. But I am going to explain also what we did before that. Yeah, somehow. Okay, so let us start with maybe the first example of really important result on that, which is you have the unitary group, so isometric group of L2, and Millman and Gromov and Millman proved in '83 using concentration measure that this group, every time it acts continuously in a compact set, there is a point which is always fixed. So there is an orbit which is only one point, always. So this is called now extreme amenability. Extreme amenability is a strong form of amenability, as you might imagine, of topological amenability, right? So actions are continuous, group is continuous, so there is their topology all the time. Amenability, topological amenability, there is several different definitions. One of them, equivalent definitions, one of them is that every time you have an action, a continuous action of the group in a compact convex set, and the action is affine, then there is a fixed point. Yes? Okay, so this is a very, very extreme case where you have this property that there is a fixed point, but one of the things the people in topological dynamics, on this part of topological dynamics, want to understand are these minimal actions. A minimal action, you might guess what it is. There is no sub-action or equivalently, or whatever. Every orbit is dense. So you want to understand them because you can split a given action into these minimal sub-actions, and then you want to understand them. And one of the things they want to understand is that the universal minimal actions, okay? Those such that, so this is written in there, such that any other minimal action is a continuous, is a G continuous image of that. This is what it says in there. Extreme amenability is the same to saying that this universal minimal flow, universal minimal action, it is the same, is a point. Okay, so how do you prove these things? Well, luckily, for some spaces or in general structures, there is this, what is called this Keck-Grip-Stofft-Dorchevich correspondence, which is telling you a procedure. And this procedure is, this extreme amenability of the isometry group is exactly the same that this approximate Ramsey thing, which I'm not going to talk about. Okay, today I'm not going to talk about that, but there is some the definition in there. You will see what is that. Okay, so what are these structures for those? What are these Banach spaces? All this is a general thing. It will come later understandable why I say general thing. What are these structures which are somehow manageable, amenable for the things we want to do? Well, there is this ultra-homogeneity, or approximate ultra-homogeneity, which is this hypertransitivity, right? So you have 2 points on the sphere, and you want to move one to another by an isometry, maybe up to epsilon, yes? Give me 2 points on the sphere, give me epsilon, and you want to move x to y by an isometry. You can extend that, and instead of talking about 2 points, you have a finite dimensional space x, finite dimensional space y, an isometry between them, and given an epsilon, you want to extend that to a full isometry of the space E up to epsilon. Yes? So this is the natural extension of this, of the transitivity. Instead of with one point and many points. Yeah? Well, and what I say is that no matter two finite dimensional spaces, well, in here I am talking about embeddings, but it is the same. So you have two embeddings from X to E. So let's do it this way. So you want to find this G, which is an isometry. And these are embeddings, yeah? Isometric embeddings. All this is about isometries. That's another story. I think nobody tried to do it with isomorphism. You could, but well, this is what I said. Again, that this is a generalization, the transitivity. Well, approximate Ramsey property, which is a finitary statement, I am not going to write it down there because it's useless now. But thinking a little, you might express it in this way. Since the slides are going to be here, are going to be online, if you want to take a look, this is in there. I think this is not important for the moment. There is a way to express that. Colorings and all this. Here, instead of a coloring, which is a mapping, arbitrary mapping, I assume that the coloring is a ellipsis, coloring one ellipsis and blah, blah, blah. Okay, this is not important, believe me. Now, well, this is what it is. A coloring, ellipsis mapping is going to be almost constant in a big piece, in a big, small piece, finite set, right? Okay, so as I said before, for these kind of spaces, understanding a little the topological dynamics in an arbitrary compact set somehow can be reduced to understanding these things. What is this isotropic quotient that we call it? And this is what I'm going to discuss. Okay, some terminology, standard one, BE, SE, ball and the sphere of E, excuse me, Hn of E is the collection of n-dimensional subspaces of E, Hausdorff distance between them, between unit balls, some metric space. Delta isometry is what you know. There are several definitions. We choose this one to be a little symmetric. So up to delta, you are an isometry, yes? Delta embeddings is the collection of all these embeddings with a subnorm, with a norm, metric norm, excuse me. Norm metric. Isometry group, yeah, that's another thing that is important, is what is the topology you are considering in the isometry group. And this, you have to use the strong operator topology, so the pointwise convergence, because otherwise, typically, this will be non-separable, will not be polished, and you are entering in something else, okay? Here always, we are going to use the strong operator topology, convergence in finitely many points. Yeah, okay. So this is a Polish group when it's separable, which is interesting for some things. And now there is this action, which is one of the actions we want to understand, which is isometry group acts on the delta embeddings by simply composition, and that's it. Sometimes I forget to put G minus 1 because otherwise it will not be, but it doesn't matter. I mean, if you need G minus 1, you put G minus 1. And on the H, so on an n-dimensional space, you have an n-dimensional space, you have an isometry, and you move it. You have this n-dimensional G, and you have G of this n-dimensional space, and this is the action. Of course, all the distances work fine. They are invariant, all the distances, because they are isometries. Yes? Distances I am considering here. Okay, and now there is this, I was presenting this in some other places, so I was using this like a, okay, so there is these two things in general, more or less for that, for this of understanding, that is, you have two finite dimensional spaces, X and Y, isometric, or close to be isometric, or, and you want to know what is the effect of them to be isometric, the same shape, the same sphere, the same unit ball, in the way you can find them inside E. Yes? So can you find them, if they are isometric, can you find some isometry moving one to another? If they are two equivalent, they have two equivalent norm, can you find some isometry that moves X to Y so that the distance between them is 2 or close to 2? You see what I'm trying to say? So is there a relationship? So I think I wrote it down here. Yeah, so it is there. So is there a relationship between these two things? How they look like to where they are in the space E. So there is this thing, placement, you are in the placement there inside E, and then there is this isometric type. Yeah? Sometimes they are equivalent, sometimes they are not equivalent. And this is what I'm going to discuss here. Okay, so how many ways? So the quotient, so the collection of placements is the quotient of H modulo isometry group. So is this small? Do you have only one? Unlikely, unless it's Hilbert. Hilbert space, it is the case that there is only one, right? But if it is not Hilbert, it is unlikely that you will have only one, but yet maybe this is compact. This is small, so maybe you can express it. You can say what is the distance. Yeah? Well, this is the same thing, blah, blah, blah. This is exactly what I said, so I'm going to go. Okay, so some comment about the quotient. The quotient is the closed one, yes? So two guys, P and Q, are related. If for every epsilon, I can move P, epsilon close to Q, yes? So these are closed orbits. ¿Vale? So, well, let's call it as it is in there, understand? So the problem, again, it is the same. So, okay. Now let's start trying to understand this in a more precise way, saying the isometric types versus the placements. So given the H, so the n-dimensional subspaces, I can move X to its Banach type, isometric type. This, I call it the tau NE. It is easy to see that this is continuous, and you can pass to the quotient, because if you have the same, if you can move X to Y as close as you wish, then the isometric type of X must be the isometric type of Y. So you have that here. You have this continuous mapping. So you want to compare this object, this topological space, with this compactum. Well, correction. Compactum is if you forget E. But if you are considering the isometric types you can find inside E, this might not be closed. Yes? In many cases it will be. So, and the first question, this is what I said, is there a relationship between the isometric types and the placements, which you might refer it as this problem? Is this an homeomorphism, an isometry, by uniformly continuous, blah, 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 whatever you want, right? Okay, so again, the same thing. Excuse me, so, okay. Good, so, related to that, because it will come soon, I guess why I am mentioning this now. There is this approximate ultra homogeneity and something a little more, although we don't know if it is not the same in the moment, we don't have examples, a little more than approximate ultra homogeneity. So you see, so here I have this thing here, formula here, so okay, so let us analyze. Now I am saying, so there is this quotient here, so delta embeddings, and now I allow to move one delta embedding to another delta embedding, if I can, by an isometry. Yes? What do I want? What I want is the diameter. So it is clear that it should be clear that the diameter of this is not 0, cannot be 0, because you might have a delta bigger than 0 isometric embedding and an isometric embedding. And of course, you cannot move one to another as close as you wish by an isometry, because if you compose an isometric embedding with an isometry, this is an isometric embedding, not a delta isometric embedding. Okay, so there is some number there. So there is a restriction of this diameter that has to do with delta. What I am asking is that this goes to 0. If delta goes to 0, this number goes to 0 also in a continuous way. Yes? Is it clear what I say? Okay, and now I'm going to jump in some unexpected place. Because I want you to see that this is just a part of something more general or more or less well understood, or quite well understood, which is the notion of ultra-homogeneous structures, or approximate ultra-homogeneous structure, in what is called metric model theory. So if you forget metric, or you take, instead of if you take metric to be the discrete one, so these ultra-homogeneous structures, I remind you, ultra-homogeneous is this strong transitivity, hyper-transitivity. Give me two finite substructures. I'm going to talk in this general way, right? Two finite substructures, give me an isometry between them, finitely generated. Give me an isometry between them. I want to find an isometry that extends that, or automorphism, or whatever. I have in mind always this isometry because I am with these Banach spaces, but in every category it will be a different thing, right? Q has this property as an order, and this is an exercise we have for the students, right? And Q is unique. This is another exercise we have, and there is this back and forth argument, right? This is how you prove that this is the only countable dense in itself without endpoints, right? Random graph also is the same. You have two finite graphs, and you have an isomorphism in between them. Then you can extend it. This countable atomless Boolean algebra, which is nothing else than in 2 to the n, in the binary tree, you consider the clopens. And this is this, or if in the unit interval, these the dyadic unions of dyadic intervals. This is what it is. And this other two, right? This rational Jurison space is also of this kind. And this finite, for a finite field, you take this f less than infinity. Okay, so what I said is that they are unique, and they are determined by the local structure, and this is what is called this Frase correspondence. Yeah? So there is these inductive limits, which are push-outs. You go there in the generic way, and at the end you get this structure. So Q is the Frase limit of finite total orderings, R is the Frase limit of the finite graphs, and blah, blah, blah. You can imagine what they are, yes? Okay, so, and then there is this other Kekris-Pestov-Todorchevich that for these structures, being extremely, the automorphic group is extremely amenable exactly when there is the Ramsey property, and in this other general scenario, the approximate Ramsey property. In the case of Banach spaces, you have the Hilbert space, which is indeed ultra homogeneous, not approximate ultra homogeneous. So asking that this is the only ultra homogeneous separable infinite dimensional Banach space is a kind of a simpler version of Masur rotation, because you are asking much more, right? You are not asking simply that you can move one point in the sphere to another point in the sphere by an isometry, but not only them, but imagine that you can do this not for 2 points, but for n-dimensional spaces. Yeah? Gurari space, that it was mentioned before, so following the same thing, Hilbert space is the Fraise limit of finite dimensional Hilbert spaces. Gurari space is the Fraise limit of the finite dimensional spaces, Banach spaces, norm spaces. Yes, you do this in a generic way and you get G, and it is unique by the same way, exactly. Unique up to isometry all the time, yes? And now there is this thing that maybe you might heard on these LPs, but when P is not 4, 6, 8, and so on, this is funny, but this is how it is. And this is rather more complicated to prove. And there is this equimeasurability principle, which has its importance by itself. And that it says that if somehow there is one there, which is important, but imagine that there is no one in there. Imagine that there is no one to what I'm going to say, because it's easier to say. It says that you have F1, Fn, and G1, Gn, which are isometric in LP. Then the joint distribution they produce, so in Rn, you have this given Borel set. Given a Borel set, then the probability of this Borel set will be the Lebesgue measure of the pre-image by F1, Fn, and the same for the G's. So what it says is that the isometry is exactly the same, that they have this joint distribution. The same. Which is kind of odd if you think, and the proof is not easy, but it's true. Okay? And if P is 4, 6, 8, and so on, it is not true. Okay, so Fraise spaces are the same because we don't know more than what we know. These are all the list of spaces known to be approximate ultra-homogeneous of Fraise. It is the same in this context because we don't have. Okay, so we know what we know, and now let's move a little, and we are not so pretentious to move one isometric embedding to another isometric embedding, but maybe we want, so this is not necessarily a point if you forget delta here, but can we say that this is compact? Can we understand what is this compact set? Okay, so, and this is the move I told before. I'm going to talk fast about this metric model theory, because this is somehow a part of that, and properties from there can be understood here in a good way, I believe, in a more geometrical way. So there is this notion of omega categoricity, which for us probably is better to be called oligomorphy. That is exactly to say that these quotients are compact. Oligomorphic means literally, I guess, few forms, shapes, and this is more or less what it says in here, right? N many points behave more or less. There are not so many possibilities for n many points, yeah? Up to an isometry, global isometry. Okay, and this is when I'm going to go to this metric model theory a little, 2 slides only, if I have time. Because it's interesting, because there is this uniqueness also, like before, with this phrase. So, if E is a separable Banach space, again, this is in general for the structures, metric structures, then this is equivalent to say that this is the unique separable Banach space, which has this thing here, which will become soon maybe understandable. This metric first order theory, the same. Okay. Okay, so before going to this, there are these equivalent things. It is the same to say that this H and this quotient is compact with the H, or with the sphere, or with the ball, or with delta embeddings, or to be omega categorical, which has a different definition, but that I think is going to come now. What is a metric structure? Well, maybe you have heard about the algebraic structure in first order. So you have these operations, relations, and constants, and this is a structure, yes? Now there is metric, there is a distance d, and you can do more things, for example, in a Banach space. So, but now the relations, predicates in there, are not going to be a subset, are not going to be interpreted as a subset of m to the n. That you might think that this is a mapping from m to the n to 0, 1. This is the same via the characteristics, yes? But now it's going to be a continuous mapping, because here there is D, well, the product D, yes? So now you are going to demand that everything you are using is continuous. Indeed, uniformly continuous, and indeed a little more, but for the moment now, this is not interesting for us. You might assume that this is the unit interval by scaling and things like that. The operations, like the sum in group, you have a group, and there is the sum. Now you are demanding which is continuous, indeed uniformly continuous, and so on, right? And what is a metric structure? A metric structure is a set with a distance and with these operations and relation, and blah, 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 but in this way. Well, you can encode, which is unimportant for us how you do it, because it's a little annoying. D has to be bounded, because otherwise it didn't work. And in Banach space, obviously, the norm, the distance defined by the norm is not bounded. So you need to do everything in the ball, in the unit ball, rescaling, which creates annoying things there, not very nice to write it down. But you can do it. Okay, the formulas. What are the questions you can express here? And you might have an answer. Well, what you do in first order is to have any Boolean, so with the and the or and the negation, you can create any Boolean operation you might imagine between 2 to the n and 2 by making composition. So you might think that the formulas are defined by considering any Boolean operation and you close it off. Now, I'm going very fast without many details, but you need to believe me that this can be done. Now, instead of doing that with Boolean operations, you do it with any continuous mapping from Rn to R. I will give an example and you will see what kind of things you can do in there. And now, instead of having quantification for every x and exist x, you are doing sup over x and inf over x. Because now the value is not, the value when you want to know what is a formula means, the interpretation is not a 0, 1 value, but it's going to be a real number. Okay, so and that's a real number, this is what I said. And now what you are going to ask, the questions you can ask is phi less or equal than r. It will come soon a little clean with an example, okay? And now you have a collection of things of this kind, phi less or equal than r, and you might ask if a structure, if a Banach space M satisfies that or not. And that's the one I wanted you to tell. So you think for a while, so this is one of them. I am cheating a little here because this thing, where is this? Yeah. So these are points. So you are allowed to use sup over the points on the structure, on the Banach space. These are points in here, but these are not points, these are real numbers. But of course, by compactness, you can do for finitely many, and you can have more and more and more. So what do I say here? So I am saying, if you think for a while, that the space E, so if E's model of that is script LP1 plus. So I'm saying that this Yj behaves like little LPK. Yes? This is what I'm saying, because I'm saying that this number here is small. So this norm here is more or less what it has to be. And what I'm saying here, that given my x1, xn, I can put x1, xn inside the span of yj's up to epsilon, which is 1 over n. This is exactly to say that this is script LP1 plus. But script LP1 plus are LP spaces. So this is a theory. So models in this context of these statements are LP spaces. If a Banach space satisfies that, it is an LP space for some mu, LP mu. So LP mu. There is a mu. Well, this is what I said. You simply, it is easy to see there. So, and this is not so important to, okay. If you think for a while, what it says in there is that the mu is not atomic. Because I am splitting every point, blah, blah, blah. So you go there and you see. This is not, again, it's not so important. You believe me. So if there is a model, separable model of that, of these two, what is that? This is a LP space without atom, and it is separable, infinite dimensional. Then it's LP of 0, 1. It's isometric to LP of 0, 1. Yes? So this is somehow can be reinterpreted that the theory of LP is this omega categorical, or that the space is oligomorphic, or that the quotients are compact. By this artificial way, with you don't see anything, but it is the same. Yeah? So analyzing the things which are true, these first order, metric first order things which are true in the space, you might say things about the geometry of the quotients, how they look like, or the topology, or the metricity, whatever you want to say. Okay, so this is what I said, that if you are omega categorical, so omega categorical is exactly to say that the theory has a unique model, has a unique Banach space, which is separable. Okay. So, and I am insisting on that because it's a unique. That's the thing, right? Okay, so, yeah. So there is this other interesting thing, which is this. Well, by the way, this approximate ultra-homogeneity is this disposition, not universal, but disposition or approximate disposition thing that maybe you are more used to. It is the same. Okay. Now I say, so approximate ultra-homogeneity is telling you you have two finite dimensional spaces which are isometric. It is telling you in particular that you have two finite dimensional spaces isometric, then you can move one to another by an isometry, global isometry. Well, this is very strong. In this omega categorical or oligomorphic structures, what you have is that if the formulas true in these finite dimensional spaces are exactly the same that the formulas true in that, not only the norms of the combination, linear combination, but other things, then you can move one to another by an isometry. Yes? So you are demanding more things. Another question is to understand geometrically what it means that the formulas in X and the formulas in Y, which are true in them, are the same. That's another story, right? This is where the story is. For example, this is interesting to know what's happening in L4 and L6 and L8. We know why it's not approximate ultra homogeneous, but we want to understand also in this way. Okay, so this is what I said. You don't need to, it's going to be here, so, and there is some well-known result in model theory, which has this interpretation in metric model theory, which is this real Nardesky theorem, which is linking this compactness of the quotients with this omega categoricity, right? It is telling you that this thing about the formulas, that there is a unique model, blah, 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 it is the same that these quotients are compact. Examples. Okay. So there is C of 2 to the n, not C of 0, 1. C of 0, 1, you will see why in a moment. Yeah? So the first try is go to the, remember that we need to understand quotients by isometry. So it is a smart move first to go to spaces where you know how the isometric look like. One of the places is LP, because we have these Banach-Lamperti. We know how they look like, so we can play with them. Another, of course, before that is Banach-Stone, the isometries of C of K. So you can go there and play with them and see if it is compact or not. So this is oligomorphic or omega categorical because it's the same. And I will explain a little why. Huh? LPs for all P's, including 4, 6, and 8. So the quotients are small, are compact. What is not true is that for L4 you can move one space X isometric to Y by an isometric, global isometry. This is not true in general. Well, and indeed you have this Bochner business, and it is also true. Once you have the first one, it is true also for this. So mappings now, continuous mapping, not in R, but in any Banach space E. If E is omega categorical, of course. The same for the LPs, and more or less this is about it, what we know. Yes, by the way, I forgot to say that these things about this metric model theory was, I was trying to understand this, and it was a student, a PhD student, which is starting from Paris, Ivory Fronto, which is a guy which is supposed to work in metric model theory, that was trying to explain me all these things. Yeah? So I want to say that. Because at the beginning it's not easy to go through these things. Okay, so it is the same. Now this is a slide where you will see the connections between this approximate ultrahomogeneity and Fraise, blah, 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 with these other things. And it is the same that is Fraise and is approximate ultrahomogeneous and omega categorical. This is a result by Valentin and student. He's not a student anymore, right? Former student. He's a postdoc, so Rincon. And I don't know why we are here. Do you remember? Yes, we had some contribution. I don't know. Okay. Okay, so let me finally, I will going to explain a little how you prove that some of these quotients are compact, and indeed you can say who they are, which is a really nice thing, I think. I like it. Okay, so you have... okay, so this was me. So there is this thing, right? So there is this important thing. So there is the unit interval minus, well, not the unit interval, minus 1, 1 to unit ball. Minus 1, 1 to the n for a given n. Remember that we want to understand the quotients. Two quotients will be the n product of the ball of C of 2 to the n, of the continuous mappings on 2 to the n, and the LPs. The same thing with the LPs. So there is a, in the case of, well, it is easy that you see and then I talk. Okay, so what is Cn? Cn is the quotient of minus 1, 1 to the n by the relation, by the closed relation x is equal to minus x. in Rn, yes? Okay, so this is compact, it is obviously metrizable. Let's call this mapping going to the quotient, this identification pi n, and let's call Kn to be the space of closed subsets, of compact subsets of Cn, with the Hausdorff, the distance between them. So if there was no identification with x and minus x, this, you might think that there is the compact subsets of minus 1, 1 to the n. Yeah? You need to have an identification, you will see in a moment. And then there is this mapping, natural mapping, which is a key. You have to find natural mappings, and that's very natural. You have n many mappings, continuous functions of norm at most 1, from 2 to the n to the real numbers. So you have this f1, fn. Indeed, since they are bounded by 1 in norm, they go to minus 1, 1. Yes? So let's call this, okay, so, okay, so let's put this, and then given some omega, or I don't know how I call it. Let's call this f, and then this f omega, right? And now I go to the pi n, and this, we call it here Cn, right? So if I take the image, let's call it im of f, this is a closed subset in there, it is compact, so this, and this is the mapping. So this mapping has all the information. So this is what it says in there. Understanding, so if I want to understand when I can move n many points to another n many points, what I need to do is to take the image, quotient out by this x is equivalent to minus x, and then I know that there will be for every epsilon an isometry moving this to another. Not only that, but also I know if I know exactly how close I can move this sequence fn's, fj's to gj's, I know exactly how the image is close and vice versa, you see? So it is exactly the same. So, and why this is true? Well, there is a similar thing for LPs, but now you are not going to get closed sets, but you are going to get probabilities, which makes sense if you think for a while. So this quotient is the collection of probabilities and random probabilities on the Cn. ¿Vale? So let me, and this will be, I promise, the last thing. Well, this is what I said. Why this ball of CO2 to the n quotient out by the isometries is the collection of compact subsets of Cn. So how do you do that? Well, this is what I said. It is easy again to see that this is a continuous and it's invariant under isometries. Right? If you compose with an isometry, the image is going to be the same. And it is onto because 2 to the n is universal for separable, for metrizable compacts. So you think a little, and you will see that this is onto. And now it comes the key part. Well, two keys. Very first of all is to know some isometries. Indeed, we know all isometries, but sometimes it's enough to know some isometries. Banach Stone is telling us the answer. How do they look like? How they are? So any isometry of C of k is of the form, it has two ingredients. There is this U, which is a continuous mapping from k to minus 1, 1. There's signs. You can perturb the sign in a continuous way. And the other is an homeomorphism of the underlying compact set. Yes? If you think for a while, if you want this quotient in general, a ball of e to the n quotient out by isometry being small, it is expected that you have many isometries. because ball to the n is huge space, and now you quotient out by something that it makes sense that you might have many isometries. So because of that, this part, if k is 0, 1, is the unit interval, nothing in there, and that's a big problem. If you think a little more sophisticated, there are these oscillations that you cannot take care of them. So in the quotient, corresponding quotient in C of 0, 1, you will find sequences without convergence and sequences because they oscillate a lot. So it is not compact. And the reason, one of the reasons, of course, is this. ¿Vale? Okay? Well, it's one of the reasons. I'm trying to be very fast. Okay, there is 1 minute, 2 minutes. Okay. Now, next thing. I said that you need to know that there are many isometries. Good. Homeomorphism of K. If K is 2 to the n, 2 to the n is the Stone space of the atomless, countable atomless Boolean algebra. So these clopens of the dyadic intervals, whatever you want to say, it's the same. And this structure is ultra homogeneous, has a lot of automorphism. So there is a lot of isometries in the, there is a lot of homeomorphisms, excuse me, very first of all, and then isometries, those who you are going to use to move one thing to another thing, yes? I'm being very fast, very blah, 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 but maybe you get this idea. It is in there, so this is what I'm saying. You need to know is that if the image is the same, then you can move F to G as close as you want. And that's key. In order to do that, this is where you are using this countable atomless Boolean algebra is ultra homogeneous in their category, right? Well, okay, and this is things, well, a small remark, if you do this for dimension 1, what you get is that the quotient is the unit interval. And if you do this for the sphere, what you get is all the compact subsets of 0, 1 that has 1 in there, which is obviously not a point, which is obviously telling you that C of 2 to the n is not approximate transitive that we already knew, right? But there is more information in there, okay? And I think this is all. Thank you very much. Well, here you have this list of things with several stuff. There is this model theory there also, if you want. There is the book of Félix and Jesus, where they are talking in some of the parts is about these Fraisel limits. They don't call it this way, but they are there also. Push-outs, etc. You can have it in there too. Okay.
We call it that way.
Ah, sí?
Chapter 6, Fraisel limits. I told you so. Questions, remarks, comments? Okay, 10 minutes break, and we thank the speaker again. Okay, our next speaker is Antonio Avilés from the University of Murcia. More or less, mathematics is like the first strongly inaccessible cardinal. No matter how you say or you go, you don't get it. I dreamed that the title of talk was Basic Notions in Banach Spaces, but no, it's Basic Notions of Banach Spaces. So who knows what's coming now? Up to you.
Okay, thank you very much. They will be basic as well, so don't worry. Okay, thank you very much. I will talk about joint work with Christian Rosendahl, Mitchell Taylor, and Pedro Tadacete. It's now getting finished, so I guess it will appear in Archive soon. So I'm going to start saying some preliminaries. In previous talks, we have been talking. People have been talking about the Borel hierarchy, and we have seen analytic and coanalytic sets. The analytic set were the continuous images of Borel sets, and their complements inside Polish spaces are the coanalytic spaces. But I will go a little bit further in the hierarchy. I will also manipulate sigma 1 to sets, which are now the continuous images of the pi 1 1 sets of the coanalytic. And once I have these ones, I can take their complements, and they are the pi 1 2 sets. And then I could take the continuous images of the pi 1 2 sets. I could get the sigma 1 3, and their complements would be the pi 1 3. And I could continue in this way. And in general, all the classes of sets that I obtain in this form, all the pi 1n or sigma 1n, these are called the projective sets in general. And just as a practical thing, because how do one usually recognize sets of this form? So for instance, take this set, the set A, of all continuous functions on the unit interval, such that every real number is the value of the derivative at some point of f. So it has a lot of differentiable points, and the derivative is any real number. So what is, and I claim this is a pi 1 2 set. Why it is a pi 1 2 set? Because if I try to transform English language into formal logic language, I will have to write the set of functions so that for every real number x, there is a y. What did I write? This is not a c. This is just in the interval 0 1. There is a y in the interval 0 1 so that f prime at y is x. And well, f prime y equals x. This is the limit at y. This is for every epsilon. This is a Borel condition, because for every epsilon, epsilon can be rational. These are countable quantifiers. So in the end, what I have here is for the set of f, so that for every x in some Polish space, there is a y in some Polish space, and then something which is Borel. So I see two quantifiers, so I have these two. And because these are quantifiers over Polish spaces, I have the one above. So this is how I see that something is, in this case, pi 1 2. So this is just counting quantifiers when you express your set in some way. Okay, so this is the projective hierarchy. And now I want to also remind what determinacy is. And to get an idea of determinacy, I was inspired to somehow to transmit here what the idea of determinacy is. I was inspired by Victor's poster. His title, if you have, I guess all of you have already gone through this poster, and the title is averages of averages of averages of averages of averages of, and then dots. So why I think this is relevant here? Because one sees this title and perhaps one poses the following question. Is it really legal to write infinite sentences? And if is it legal, I mean, what are the logic rules that I should use to operate with infinite sentences? Okay, let's see what I mean. But the answer I'm going to give is that I think yes. I think that Victor is fine to do this. We can tolerate his behavior. So if you have, imagine that you have a subset of sequences, a set of sequences of natural numbers, a containing n to the n, and then you play a game that we call G of A. And this game considers there are two players, player 1 and player 2, and they alternatively play natural numbers. And when they play these natural numbers, in the end, they produce a sequence of natural numbers, when I put all these numbers together. And we say that in this game, player 1 wins. Let's say player 1, if the sequence belongs to the set that I fixed at the beginning. Otherwise, player 2 wins. And I say that the game is determined if one of the players has a winning strategy. So a winning strategy is a kind of book of instruction that tells, for instance, for player 1, that if it's for player 1, it's that it tells player 1 what to play first, and then depending on what player 2 wins, his book of the instruction book tells you what to play next, and then depending on the next move and so on. But you could if you want to write infinite sentences in Victor's way, you can write this fact that one of the two players has a winning strategy, because you can say, what, you see, there exists an n1, so that for every n2 there exists an n3. This is a winning strategy for player 1, because it tells you player 1 can choose a number n1, so that for every move of player 2, there is a move of player 2, player 1 has a move again, such that blah, blah, blah. In the end, n1 and 2 belongs to A, because this is what player 1 wins. And I'm saying that if player 1 doesn't have a winning strategy, then player 2 has. Here I fail already. Also, there is a no here, because when you negate, you have to negate the last thing, but I forgot, okay? But you, you know the rules. So the statement, one of the players has a winning strategy, is the statement that you can use negation rules in infinite sentences. It's, and can you do that? So is it really, when you manipulate sentences, can you really manipulate infinitely many quantifiers? Okay, it depends on the set A. In general, if you love the axiom of choice, if you don't want to, you know, if you don't want to live on Han Banach and these kind of things that you like, then you cannot say this in general. Then not every set is determined, and so you cannot make this quantifier change with an arbitrary set. On the other hand, if the set A is nice, if it is a Borel set, then there's a theorem that the game is determined. So if this A that you can view it as a sentence at the end is nice, is Borel, then this works. You can operate in this way. If it's Borel, it's not Borel, but it's still analytic or something like that, then you don't have theorem, but there's an axiom. You can see this. It becomes something that you cannot prove from CFC, but that the logic community accepts as something that they allow you to assume as an axiom. So this is the axiom of analytic determinacy, that this game is always determined whenever A is analytic. You could also state an axiom of sigma 1, 2 determinacy, of sigma 1, 3 determinacy, depending how far, or even projective determinacy. According to, we will use this axiom at some point for some of our results. And the comment of Christian Rosendahl is, okay, it doesn't matter if we have to assume this kind of axiom, because this is like the natural axiom from mathematics. It's like, it's okay to assume this. This is his point of view. And if you allow me to say some stupid story to, I would give an argument for that. I don't know if you know this story by Herodotus, the Greek historian, that Pharaoh Psammetichus wanted to know what was the first language spoken in the world, what was the first language. And the experiment consisted of taking a little child and growing him with a ban on talking to him. Nobody could talk to the boy. Well, two boys. And they will all be pay attention to what is the first word that he produces by himself. And whatever language that means that this is the right language. They claimed it was a Phrygian word, so Phrygian is apparently according to this. Okay, why I said this stupid story? Because an argument for saying that this axiom is the right thing is that our little kid is Victor in this case. If he, by himself, decided that he can operate with infinite sentences and this is fine, this is a proof that this is a natural axiom that comes out of human. Okay. Now we can go back to mathematics. And to Banach Spaces, because this is a conference on Banach Spaces, I was just making some preliminaries on set theory. Okay, let me remind that if I have a filter, there is a notion of convergence of a sequence through that filter. Filter, when I say they're a filter, I mean a filter on the natural numbers, a filter of sets of natural numbers. And this means that xn converges to x in any topological space if for every neighborhood of x, the sequence enters in the neighborhood filter many times. So if the filter is like the cofinite says, this is usual convergence because the sequence gets except finitely many. Otherwise, okay, you take a filter, you have a convergence. And the idea of Vladimir Kadets was that perhaps you can create a notion of basis that corresponds to such convergence. And then simply you would call, if you fix a filter, you will call an F basis of a Banach space is a sequence of vectors. So that one of the ways of viewing a Schauder basis, for instance, is that every x is expressed as a series with some coefficients in a unique way. And then after that, you can start from that definition, you can prove all the other properties of Schauder basis. So he just changed that the convergence in the series, in the limit of the partial sums, is filter convergence. Okay, so he tried to develop this theory. He had some papers with several co-authors on this topic, but he left some open question that was puzzling for him and for his team. And this is, okay, when you use Schauder basis, you start from this definition. You can later prove using uniform boundedness principle that the functionals are continuous. But if I only have filter convergence in this definition, can I prove that the coordinates are continuous functional? From this, you derive a number of things. Okay. The first answer to this, well, there were some partial answers before by Koharnek, but the first general answer to this was by Kanya and Svachina, and they prove that if F is a projective set as a filter, so if it is more or less reasonable set that you can describe with some quantifiers, and this covers the examples that Kadets had in mind because he didn't want to apply this to some set theoretic filter, but I don't know, statistics, convergent filter, or things that you define. They said yes. And okay, they applied some heavy set theory, let's so to speak. It's not a long paper, and perhaps for expert in set theory it would not be so scary, but perhaps for was coming from Banach Spaces the problem. Some model L of R, many wooden cardinals, okay. Later, they collaborated with de Rancourt to say, give an answer yes if F is analytic, where they didn't need the so scary set theory. So, for instance, don't need to assume that there are large cardinals and so on. Nice, short thing, but still a little bit handmade things. And then last spring, I was in May last year. I was in Canada. I was in Toronto, and there was a program, one of these programs in the Fields Institute, and I was there, and okay, why? What happened here? Okay, everything is like this. There was Christian there, and he approached me during a coffee break, and he told me, look, I think I can do this stuff of the continuity of the functionals using some machinery from topological groups, which makes things, in a sense, it's like the things that these guys have been doing handmade can be derived from general theorems on topological group theory. So these guys knew a lot of set theory, but perhaps they were not familiar with this stuff, and then they could have gone faster if they had applied this. And let's see the argument. The argument is very nice and very short from general theorems that are quite intuitive or quite. So what is the thing? The thing is, okay, you have this basis, this F basis, and you have these coordinates that you know that for every x has a unique coordinates for a certain expression, and then you consider the mapping that applies to every element of x, the sequence of coordinates. It goes from your Banach space x, and we are assuming that the Banach space is separable. Sorry, I think I didn't say, but well, it has to be in this moment. And this is a group homomorphism, when the group operation here is the addition. Addition in the Banach space and addition coordinate by coordinate. And okay, I want to prove that this is continuous, because if I want to prove that this coordinate is continuous, the same as to say that the product is continuous. And you have this nice theorem. Depending where I read it, give different names, but at least in some places it is a corollary of something by Pettis. A group homomorphism between, in this case, Polish groups. It has even more general framework. Groups that are Polish spaces where the operation is continuous. If and only if it is bare measurable. The preimage of open set is a set with a bare property. So in order that you prove that, thanks to this theorem, in order to prove that this is continuous, it's enough to prove it's bare measurable. You don't need exact continuity. So this is a kind of automatic continuity theorem, it's called. But there are also, if you want to prove that something is bare measurable, you have theorems telling you that look at the function between Polish spaces, look at the graph, compute how complicated is the graph, and if it is not too complicated in the hierarchy I described, then it's going to be bare measurable. And in this case, the graph is the pairs xy, so E of x equals y. And because these AKs are the unique scalars which give the series, then saying that E of x is y is the same as to say that y is the series through the limit through f of the corresponding sums, okay? But then it's easy to see that if the filter, for instance, is analytic, this expression becomes analytic. So the graph is analytic, and there is such a theorem that if the graph is analytic, the function is bare measurable, and therefore by Pettis' theorem is continuous, and this is the argument. Very nice. Okay. Then after after being in Toronto, I went to Madrid to meet the Banach people. Let's recall what the Banach is. Banach people, I mean Pedro and Mitchell, the other co-authors of the work. Banach for those of you perhaps that may not be completely familiar, this is just a Banach space where you also have a partial order, less or equal. The typical example are all the classical spaces that are made of functions, where the functions have a natural order, pointwise order, or pointwise modulo null set order, like big L1 or something like this, or big LP. And you put some reasonable actions, that it is a lattice, which means that every couple has a supremum and an infimum. And I could put a list of actions, but I can simply say that any inequality that you write that is true for all real numbers, where you put linear operations or these lattice operations, if it is real, if it is true in the real line, it's true in the Banach lattice. So this could be your list of actions without writing list of actions. And the last action it has, because it's Banach space as well, I have to relate the lattice and linear operation to the lattice operation to the norm. And for this, I define the absolute value, which is, what is the absolute value? The maximum between x and minus x in the real line, but here I say supremum. And the relation with the norm is that whenever I have vectors that in absolute value, if the absolute value increases, the norm has to increase, which is what happens in all natural like spaces of functions, C of k, LPs, or whatever. This happens. Okay. And then I'm going to present what is in the title of the talk. Convergent notions in Banach lattices. So what do I mean by this? First of all, I have this is just a notation to make these definitions that I'm going to go to write later easier to see. First of all, what does it mean? If I have a sequence yn in a Banach lattice, I say that the vector z is an, it says in, not in, an, sorry. I finished my slides at 6 a.m. this morning. There are some mistakes. So z is an eventual upper bound of yn if from a moment on the sequence yn gets below z. So it means it's intuitive what it means. This is eventually becomes an upper bound. Okay, so now let's write. So first of all, what does it mean that the sequence in a Banach lattice order converges to a vector x? It means that when I look at these eventual upper bounds, I have many, and they become as very small. They become the infimum of this eventual upper bounds is 0. This is what order convergence means. There is a variation of this, which is sigma order convergence. In this case, it's similar, but I demand the supremum to be reached by the infimum of this eventual bound to be reached by a sequence, by a countable set. And finally, I have this uniform convergence. In this case, this is its time is stronger. Because now the sequence, because then again I have a sequence of eventual upper bounds, but these are a fixed vector that I am dividing by 1/2, 1/3, 1/4, and so on. So it's like I have, if you think of this as functions, it means that there is a function. You think of your Banach lattice as functions. There is a function so that its multiples catch the sequence going to 0. Okay, the multiples going to the scalar multiples going to 0. So here, like the convergence is located below a given function, while in the other cases it can be, so to speak, spread. Okay. Okay, so people have been manipulating this kind of convergences in a Banach lattice because we have this order, we have more notions than in Banach spaces. And an observation is that these definitions, they are called convergence notions, and they are not called order topology or sigma order topology, because really these are not the convergence notions of a topology. You cannot define a nice topology that makes these the convergence sequences. It's in this case, even if we are so happy with the axioms of topology that seems to deal with all possibilities of convergence, in this case, this is not the case. This is not really. So we need to. They can be generalized to nets. You can make them. You can put these definitions into convergence of a net, but still it would not be. It would be a natural notion of convergence, but it would not be derived from a topology. Okay, and then these people, the Banach lattice people, some of them, they have been considering an idea similar to cadets, in a sense, independently, to say, okay, let's consider bases just adapted to this convergence. So it's like a similar idea. So, and then, okay, I will mention the people later, but the notion is just that I say that they have some vectors n. I will say they form, I call that C basis. C basis could be U basis, O basis, sigma O basis, depends on the convergence. If every x has a unique expression as the limit in the sense of the C, whatever C is, any of these definitions, of the series expansion. So it has a unique series expansion, but then when I take the limit of the sums, I mean the limit in this sense. Okay. And again, they have the same problem. Indeed, the intra-story that I could learn is that these people, Gumenchu, Karlov, and Popov, they kind of, when they send their first version for publication, they kind of, without being very careful, they kind of thought that the functional should be continuous and that this was something like obvious. But it was noticed by some referee, that it was not me, I can say, that here there's a proof lacking. And because they were not able to fix it, they had to put this kind of notion in their hypothesis for the theorems or in their definitions to make their theory work. But they didn't know if the coordinate functionals are continuous or not. But actually then when I was coming to Madrid and talking to these people, I said, well, but come on. I think the same argument from Christian could be applied here. We can just make the same thing. You take, assume again, and now assume that X is separate, because here, this notion of basis could make sense even for a sequence, but the space not being separable, because these convergences can converge. For instance, if you think of the basis of the unit vectors of L infinity, you can get every set is like the supremum of some set of vectors. And here this order convergence corresponds to taking supreme and so on. So, but here we're going to assume separability to apply this kind of techniques. So we take the evaluation operator, and again you are in the graph, if and only if, because this is by definition the unique expression, so being in the graph means that y has to be the limit in the sense of C of this series. So now what we have to check is, okay, look at each of these notions and compute the complexity of this. So just write the thing and count quantifiers. Because discrete theory is very easy. You just do this. Apparently, this is this is the easy part, of course. Okay. So again, if the graph happens to be analytic, then we just would be in the same place as before. Okay. So let's check. For instance, let's take U convergence. If I don't, I remind. U convergence was this thing that I have eventual upper bounds or where the multiples of a given vector. This was uniform convergence. So then, what does it mean that y is the uniform limit of the series? So uniform convergence was there exists a vector. Fine. And then, because I had said over M, this is now a countable quantifier. And eventually means that there is some numbers that after that, that happens. And this is continuous stuff, inequality, summing. So this is one quantifier exists over Polish space, and the rest is Borel. So that is sigma 1, 1. Sigma 1, 1, one quantifier over Polish space. The graph is analytic. So this is what we wanted, and the thing is continuous. So, in fact, uniform bases have continuous functionals. So you can go back to the original version of the paper of these people. Okay, let's go have a look at the others. Let's have a look at for instance, sigma O convergence. This meant that the eventual upper bounds, I have to have a sequence with infimum 0 above it. Okay, so what if I try to write it? So you are in the graph. You are in the graph. If and only if y is the limit in this sigma order sense of sigma k. What does this mean? It means now there exists a sequence of elements with infimum 0 and says that the sums eventually get inside any ZM. Okay, so now I have two conditions. On the right, beautiful, Borel, because everything here are natural numbers. On the left, I have the condition infimum of a sequence is 0. But again, we have to, if we want to know how complex this is, we have to skip, the translating into decodifying into computer language. Okay, so the infimum condition, what happens? Infimum is 0 means that there is no lower bound bigger than 0. It means any vector, any positive vector is not a lower bound. This gives me a for all positive vectors, a for all quantifier over a Polish space. But this is inside an exist, which was before. So what I get two quantifiers over Polish space, starting for exists. So this is sigma 1, 2. Apparently, this is sigma 1, 2. The graph from the computation, if I look at the definition, the graph is sigma 1, 2. Do I have a theorem for sigma 1, 2 that implies what I want it to be very measurable to apply automatic compatibility? It's not true in ZFC, but if I assume analytic determinacy, I mean, if this kind of theorem, if I want more complicated sets to produce bare property, what I need to assume is that I assume more determinacy on sets, more possibility to exchange quantifiers when negating. So under analytic determinacy, and also if you don't like determinacy, actually this is also true under MA at not CH. This implies that E is bare measurable, as I said, and then again it is continuous. So in this case we get, okay, a theorem, but with some set theoretic. But remember also Rosendal's statement, these are the kind of actions that you should not be afraid to assume, because these are kind of the right actions, not the. So if we believe him, if we believe Sameticus method, we are happy with more or less happy with this. Well, if I'm not going to repeat the operation, but if I look at this order thing, what I get is pi 1, 2 set, so, which means that I need to assume sigma 1, 2 determinacy to get the result. So I have to even push this further into the projective hierarchy, the determinacy, if I want to obtain the result. So even more ghost-like set theory. Okay. So this is where, but okay, I said we should, okay, there is this kind of thing that, yes, this is the right, but we all know that people are not equally happy with ZFC result, or with, you have to assume something. So do we really need to assume determinacy for these results? And as I said, the easy part of the script set theory is, okay, I just have a definition, I see how it looks like, and I count quantifier, I say, okay, this is pi 1, 2. But this doesn't mean that it cannot be something simpler. Perhaps there is another equivalent way of defining the thing, which makes it analytic instead of quantitative. So here, how is it possible that perhaps like the straightaway way to define this thing needs this action, but perhaps if there is some other way to rephrase it that makes it sigma 1, 1, and then I don't need the actions. Okay, so where did the extra quantifier, annoying quantifier, come from? From this set, from the infimum 0 definition, that it was co-analytic because it has this for all, you are not a lower bound. Can I remove this? Is this really true? Is this really co-analytic, or there is another way to express infimum, which is actually Borel? Because if it's already co-analytic, if it's analytic, it's Borel. Okay, we don't know. Well, no, we have not been able to figure out this. But we don't know. Okay, but we know something. I will write it what we know. I know that if we take all the pairs given by a Banach lattice X and a sequence, say, of positive elements, and those pairs of sequences in a given space whose infimum is 0, we know that the set is not co-analytic. And here, I am defining, I'm talking about the co-analyticity of a set of pairs. Here I have a Banach lattice, separable Banach lattice, and here I have a sequence in it. So here, what I'm using the analogous of Bossard theory. In Bossard theory, you know that when you have Banach spaces, you can view them as points in a Borel space. And then you can say it's a family of separable Banach spaces, analytic. Analytic, this is what has been explained here, I think actually in more than one talk, in Gilles' talk, I think, and I don't know if somebody else talked about this. But this theory, this Bossard theory, has been also transferred or generalized or in the concept of Banach lattices in the PhD thesis of Angelica Tursi. And you can operate in a similar way as you operate with Banach spaces. So it makes sense to. So what is the difference between what we have here and what I was asking there? That here I'm saying, okay, infimum 0, if I view infimum 0 like in all possible Banach lattices as a global thing, that's true coanalytic. But that doesn't mean that whenever I pick a particular Banach lattice and I look at the sequences with infimum 0 in that particular Banach lattice, perhaps it's always Borel for every particular Banach lattice. Because here, take into account that the infimum, it's not the same having infimum 0 in X than having infimum 0 in a bigger Y. Because perhaps in X you don't have lower bound, but in the bigger Y there's a lower bound. So it's not, you cannot consider it in a universal space. It changes with the space. How I'm going time. Too much time. Okay, so I'm giving a name, provisional name in the talk for this set, the order null sequences. I could talk order null sequences, sequences whose infimum is 0. Is Borel in the following cases, for instance. There are some cases in which we know that it is Borel. One thing is if X plus has a countable pi basis. And pi basis, I mean, if you know the notion from topology, I'm using something analogous. A pi basis is a set of positive elements so that every other positive element has one below. So this typically things in spaces, this countable pi basis typically happens in spaces of sequences because the unit vectors of the sequence, they are below any, well, they're rational multiples are below any other vector. So these are spaces with, if you have such a thing, countable pi basis, then where you don't have countable pi basis in things like measurable functions, where in L1, big L1, then you don't have this kind of thing. You have, but in this case, well, and this is simply because this is an easy observation, because if I have a countable pi, to know if an infimum is 0 or not, to know if there is a lower bound, I just need to look if there is a lower bound in the pi basis, because if there's general lower bound, there is a 1 from the pi base. And then and in this way I transform a quantifier into a countable quantifier. So this is a simple trick to have a case where we don't need axioms. And the other is there is other property that's called Fatou property that might remind you of Fatou in major theory. And this is a property of a Banach lattice that says if I have an X that is the supremum of an increasing sequence of positive elements, then there is a continuity in the norm. The norm is the supremum, the norm of the supremum is the supremum of the norms. Also reminds of Lebesgue domination theorem. Well, I'm not going to make here the computation, but it's an exercise to see that in that case, one can rephrase, with this property, one can rephrase having infimum 0 into a Borel. But what we found is that we can generalize this Fatou property putting an ordinal parameter. An ordinal parameter. So it's this Fatou, one could call now it 1 Fatou. And then we could define 2 Fatou, 3 Fatou, omega Fatou, omega square Fatou. And this will define some kind of, well, I'm not sure if to use the word rank because now I'm feeling unsafe. But yeah, I think so, because it characterizes the Borelness of. And this alpha Fatou thing is the thing that is going to tell you that the thing is coanalytic. And this is about having approximate low, because here the negation of this is that you have a lower bound. If you are not infimum 0. But then you can think of having approximate lower bounds, in which you start with no lower bound, which is epsilon lower bound, then another a little bit better, and then another little bit better. And then if you think in terms of trees or in terms of gains, how much you can, how deep you can go producing this approximate lower bounds that try to converge to an exact lower bound, you get some ordinal index. I don't want to make here technicalities, but this is the idea. And we know that alpha x is alpha x is, this set is Borel if and only if the x is alpha phi2 for some alpha. There is some countable ordinal which controls how you can approximate lower bounds from approximate lower bounds. And the result I said before is based on, oh sorry, this is not written here, is based on constructing for every alpha a space which is not alpha phi2 but still has Borel index. So it means that all these classes are, it's not true that all spaces with Borel order null sequences are alpha phi2 for a given alpha. You can go, the alpha can be as large as you wish. And this is why this family is not coanalytic. This is what's going on. So it's based on and on finding that there is this hierarchy which goes up to omega 1. But we don't know if this hierarchy covers all Banach lattices. This is the point. We don't know if every separable Banach lattice is alpha phi2 for some alpha. We don't know if there is some Banach lattice for which this set is not Borel. This we don't know. We are not able to. We are not able to put all the bad things in the same space. We are able to produce as bad things as we wish, but it's time in a different place. Okay. Let me state here some of the theorems that we derive from our results, and not exactly from what I said before, but from the same techniques that I mentioned before the other paper. This is another paper by Taylor and Trotsky where they also consider this kind of basis, and with these techniques we are able to solve a number of problems that they were not able to solve with the usual techniques they were manipulating. And one of them is the relation between these different kind of bases, which is tricky, okay? Which is that if we have, under this assumption that we are in a separable space where this candidate to a basis is linearly dense, and if I fix possible functionals, these functionals are not assumed to be continuous, are these possible coordinate sets, then if you have an order basis, then it implies that this is a sigma order basis, then it implies that this is a U basis, and it implies that this is a Schauder basis. So you have this scale. And the other result, which is also kind of nice, is about this U basis. Actually, the U convergence is in a sense, from all the convergence I said, it has one thing which makes it more natural than the others, is that this order convergence and sigma order convergence depend on the ambient space. You can be order convergent in X, but you view a larger space Y and not to be, or I mean, it depends where you live. But the uniform is independent of, it's not obvious at first sight, but it happens to be independent of the ambient space. And there is a way to characterize when a sequence is a uniform basis. It's basis in this uniform. Again, under this assumption that the elements are dense in X. This is stupid what I wrote here. Forget it. Of course, it's not the equivalent to be a Schauder. I don't know what I wanted to write here, but it was not. So forget number 2. 1 and 3 is the important stuff. I think there was a sentence that was to be continued, and I forgot to continue. Here, what do we have here? Let's have a look at this inequality here. This is a variation on the basic inequality, because what I have here is the norm of a certain linear combination. And here I have the norm of a shorter combination with less number. This is, for instance, up to 8, and this is up to 5. And you all know that the projections on the first coordinates are continuous and actually are bounded by a uniform constant, this constant m. If I don't have here the supremum, I'm just saying that there is a basic constant. But of course, if I have this inequality without the supremum for all k, I could write the supremum outside. Because if you are all the time the inequality, you can put the supremum. And here what we are saying is, okay, the difference between Schauder basis and the uniform basis is that this supremum that you, in the Schauder basis you have it outside, now you have it inside. supremum of, if you think that these are functions, you have a supremum of functions. And for instance, you have these kind of things in some natural bases like trigonometric basis and this stuff. Actually, some of the arguments that they give to have the number of properties, the name of the kind of conversion they have, mean that they are of this sort. Okay, so this is again there was some missing link in this thing. Again, concerning in the original paper, I mean, again concerning the continuity of the functionals, it was the main problem. But with this thing that we are doing here, this gets solved. And this, okay, okay. There are no more transparencies. It's 47, so it's 3 minutes to my time, I think. So I think it's a good time to finish. Thank you very much.
I just want to ask, are there any good examples of those bases in classical spaces, like non-trivial, maybe?
Yes, this was what I was saying now. For instance, unfortunately, I don't have this now by heart in my mind. But for instance, the trigonometric series, for instance, when you prove that it is the convergence, because in principle the convergence would be in when you write it, say in L2, it's in principle a convergence in L2, but then later it becomes in I don't remember these things now, in measure or. Okay, sorry that I don't know this by heart, but.
So what is trigonometric system is? Like, what type of basis, like, for trigonometric one?
Yeah, I mean the classical sines and cosines, and for instance, would satisfy.
Those are like basis for like LP, right?
Yes.
In terms of new notions, like, what do you know about trigonometric system, for example?
Yeah, the trigonometric system would be a U basis. Yes.
Any other question?
Can you explain the first item for the theorem above? I mean, what do you mean by this implication?
Oh, simply that if I have a sequence, En of vectors, and given functional coordinate functions, then if these vectors with those coordinate functions are an O basis and an order basis, then they are a sigma order basis as well, with the same coordinate functions, as far as I assume sigma 1, 2 determinacy.
So shouldn't you you put the opposite implication? Sorry.
I think it has to be like this. The point is that one thing is that the convergence goes in one direction, and the other thing is when you say that it is a basis with respect to that, it means that every vector has to be the limit of that, so this makes things go a little bit the other way.
And do you have, well, you don't have any model theory where this analytic determinacy is not true,
No,
you have the opposite result.
No, we don't know if this could be true in CFC in general. This is the kind of problem I was saying, that perhaps things are more simple and you can remove.
Gracias. Antonio, in the classical case, if I remember properly, the continuity is obtained using, well, it depends on the books, of course, it depends on but using closed graph theorem.
Yes.
You, if I understood you properly, you are using these statements about automatic continuity of measurable map.
Instead of the graph to be closed, now it's only analytic.
No, the question is, it should be possible to use only closed graph theorems in the things that you have done?
I don't think so, because if I already have to sweat to get, I'm not able to get analytic and I'm sweating, I doubt that I can get closed.
No, okay. A closed graph theorem in the statement that you need. I mean, if this is, has closer graph than continuity, instead of measurability continuity.
Yeah, but what I'm saying is closed graph is a very strong condition for the kind of things that we have here.
Okay.
It's too much somehow.
Okay.
Any other question?
Do you remember what is in 2? What do you need in 2?
Ah, what was 2? Here I have it. What was in 2? Well, yes, that it's with coordinate and that these partial sums are order bounded. This is it is Schauder basis in which the partial sums are order bounded. If the partial sums are order bounded, then they already converge. Yes, sorry.
Somebody else? Okay, then we'll make a break until 11:30. We'll continue at 11:30. Thank the speaker again. Are we ready?
Yeah.
Okay. We start again. Our next speaker is Wisław Kubiks from the Institute of Mathematics in Prague. Is the living proof of what Sting says in a song. You can take among whatever you want, but not the mathematics. So, up to you. We'll talk about generic linear spaces.
Yeah, okay. Thanks, thank you. So first of all, I would like to thank the organizers for inviting me. I am very happy to be here again after a long time. And I put the title Generic Linear Operators, although to be honest, I would maybe emphasize more generic Banach spaces, and operators come like on the side. But I don't know if this is visible, what I wrote. So I have to say that I'm working for more than 10 years, more than 15 probably, in this Fraser theory, very abstract Fraser theory. Even though if you will see on the slides the name Fraser doesn't appear at all. But I'm going to mention him anyway, many times. And I will start by arguing with Jordi's lecture. So just want to say that Fraser theory is part of category theory, not model theory. But at the beginning, so I use very basic things in category theory. The most sophisticated thing is probably the push-out, which is a special amalgamation. And yeah, let me explain this a bit. So in my opinion, of course, this is my personal opinion, model theory gives too much noise. Fraser theory is about homogeneity, approximate homogeneity, universality. Everything, all these things are explained, you playing with arrows, And, but yes, you may complain. We are in Banach space theory here. So there is this problem that homogeneity is approximate, etc. So, but I didn't write pure category theory. So trying to write big letters so that it is visible. Metric enriched category theory. And what does it mean? I'm talking about this because maybe my slides will be more understandable, that everything what is behind is category theory and very basic things like chains or functors from the natural numbers into some category and push-outs occasionally. So what does it mean, metric enriched? That normally a category consists of home sets, right? You have you have any two objects, A and B, you have something like, let's say K is the name of a category. Yeah? So K of A, B, some people would say HOM, HOM, or whatever. There are several notations. More economical notation is just using the name of the category. These are all arrows from A to B, right? And so this is a set. Normally this is a set, and the main thing in category theory is that you have a composition operation, right? So it goes through, now what? You are from somewhere to A, yeah? So maybe C, A. From somewhere to A, and then from A to B, it goes into, now I'm running out of space, but it's going to, the domain is C, codomain is B. And yeah, and you have associativity, and you have identities, of course. What does it mean, metric enriched? Simply, all these sets are not just sets. These are metric spaces. And actually, for phrase theory, we need complete metric spaces. So I could even say complete here. Because we want that certain sequences converge in the end. So these are metric spaces, and what do you require? You require that the composition is non-expansive, let's say in both coordinates. Okay, and then this is called metric enriched or complete metric enriched if the spaces are complete. And indeed, if you take Banach spaces, linear operator, let's say of norm at most 1, oh, the norm 1 is actually important. Then this satisfies this axiom of metric enriched. Okay, there is a general like enriched category theory. There exists something like that. It was developed by Eilenberg in particular, I think after MacLean. And it's becoming sometimes very technical. This is something very simple, I must say. So, okay, basic examples are, as I said, Banach spaces with operators of norm 1, metric spaces or complete metric spaces, if you wish, with non-expansive maps. Yeah? So this kind of thing happens. Okay. Let me just write this thing, maybe one aspect, what you can do with this. Once you have a metric enriched category, you can consider non-commutative diagrams. So, for example, you have some object, you have some arrow into another one, and let's say, okay, maybe something like amalgamation. You can say that this is commuting up to epsilon, right? Namely, going this way and this way we make epsilon error. It is legitimate because we are in metric spaces after all. Now, the axioms, which I didn't write, I only said more or less, yeah. The axioms allow us to kind of sum up diagrams, okay? Let's say that, for example, this diagram is delta commutative. Once you erase this, you will get epsilon plus delta. Okay? This is what is more or less behind. And this is the most important feature, I would say, because otherwise you cannot survive, yeah, with this. And then, for example, you have a sequence. The sequence is a functor from the natural numbers, yeah, and here you have some object, and you have, normally, if I draw an infinite diagram like this is called a cone over this sequence. But I may consider something like Cauchy cone, namely that for every epsilon, I can cut this sequence in such a way that everything above is epsilon close, yeah? That this commutativity is up to epsilon. And in that case, once you have something like colimit, you still have a unique arrow which completes this diagram. So these are the features of metric and categories. So, but now maybe let's forget about it. Let me go to the subject of this talk, only that these tools are behind is what I'm going to present. So I'm going to talk about joint work. I forgot to write in progress with my former student Joanna Garbulińska-Węgrzyn and my old colleague Sławomir Turek. And but I'm going to present also some results from my older papers, yeah, about generic spaces and operators. Okay, now I started with hiding category theory, yes, but this K, Gothic K, is nothing but a category of finite dimensional Banach spaces. So with certain isometric embeddings. So we can, for instance, take your favorite finite dimensional spaces, yeah, maybe Euclidean ones, or maybe finite dimensional L1, or etc. And either you allow all embeddings between them, or maybe only some embeddings. Okay, well, category theory can accommodate everything, so no problem. Now, I wanted to define the notion of being generic. First, generic space. So this is what I call Banach-Mazur game. And if you look at it carefully, it is clear that actually this is a purely category theoretic concept. We are playing, two players are building a sequence, like on this picture. E0, E1, E2, etc. Forget about this blue, maybe. Erase this, yeah? Okay, and they are obliged to play in this fixed category K. Okay, now, okay, that up to this point the game is just for fun, yeah? We need to say who wins. So the second player wins if the completion of this sequence chain is isometric, linearly isometric. I'm going to talk about isometric theory, okay? Everything is up to isometry and everything is about separable Banach spaces and operators. And but again, this completion of this union is nothing but the co-limit in the category of Banach spaces and operators, yeah? Non-expansive typically. Okay, I will mention it later again. So we have this kind of game. It is like Banach-Mazur game because Banach or Mazur actually invented this game with open sets or open intervals, in fact. And if you put a suitable topology, it would really reduce to this game, but it's not needed. Yeah? It's like a very abstract notion. All right, now a space is generic, K generic or generic over K, if the second player has a winning strategy. Yeah, typically you would expect that being generic is like being residual in a reasonable topology. Yeah? So there is a reasonable topology indeed, such that genericity in the sense of the game is like being generic in the sense of the classical Banach-Mazur game, and this means being residual. Isometric copies form a residual set. But I would like to avoid these things, yeah? Not too much topology. maybe partially because of time. So, yeah, once you have fixed this category of Banach spaces, a generic space may not exist, of course. Hard to find examples, actually, but there are quite many open problems here. However, once it exists, it is unique. Do you agree? I suppose you can see, because the game has equal rules, yeah? I mean, for both players have the same rules. The only thing is that the first player, if, starts with something. Okay, so maybe we have some bad class that her first move may be problematic, yeah? But otherwise later she can use a strategy for the generic space. So let's say if there are two, the second player uses a strategy for the first one maybe, and the first player for the second one, yeah? And they both win. So must be unique. Okay, so in any case, the Hilbert space is definitely generic, and it is almost trivial. The two players are playing with Euclidean spaces, so it's enough that they are adding more and more dimensions. Yeah? Never stop, yeah? To get an infinite dimensional space. And so this is obvious. And now comes the space which was already mentioned by Jordi, I suppose, or not, the Gurari space, yeah? For sure it was mentioned. This is really the Fraser limit of all finite dimensional spaces. But I would put a little bit lesser known definition. It's not the one which Gurari gave, but it avoids epsilon isometries. So maybe on the picture, it is the most complicated separable Banach space, yeah? And it has this property that you give me any finite dimensional space, any finite dimensional extension of it, so making some small error, epsilon error, I can find a copy of this, yeah, which is close, maybe F tilde, yeah, is what it says. The original definition of Gurari was different, that you can find an epsilon isometric embedding which really extends the original one. And this is equivalent, although it's not trivial that it's equivalent. So there was a long, maybe not long, 10 years waiting problem whether the Gurari space is unique up to isometry. It was solved by Wolfgang Lusky 10 years after Gurari's paper. So Gurari was 65, Lusky was like 75 more or less. Yeah? And through category theoretic Fraser theory, I was able, together with Sławek Solecki several years ago, to find a purely elementary proof. Okay, our paper was accepted too early, too quickly, because our proof is not elementary enough. We've been using functionals, okay? There could be something. Okay, I will tell you maybe what is the crucial thing behind this, something like correction principle. Correction. I don't know what's a good name actually for this. The point is that you are having some epsilon embedding. Let's call it F. No, it doesn't matter. So you have some mapping between Banach spaces which spoils the norm, yeah? maybe extends by 1 plus epsilon and or decreases by 1 minus epsilon. The point is that there exists some norm on the union, or on the sum, sorry, such that there are some embeddings, really embeddings, such that the error is epsilon. You can correct epsilon isometry to an isometry, but making not a big error, yeah, the same epsilon. Would be okay if it was 1 million times epsilon, no problem, but should be just depending on epsilon, not on x, y. This would be too bad. So this is what is behind what gives you approximate homogeneity, etc. These things what Jordi was telling about. So, yeah, so that's, and this, there is this result. Actually, sorry, many things are missing on my slides. I wanted to say that if you have a separable Banach space which is approximately homogeneous, so those of you who attended Jordi's talk should remember, but I can maybe describe it. Then, in this game, you have a winning strategy for this space. So this is really a special case of some probably more general result, except that we do not have many examples. Yes, it's capital LP, where P is not even, and the Hilbert space. Okay, so this approximate homogeneity, which really follows from the condition, is simply you have two finite dimensional spaces, say E0, E1. You have an isometry between them. Maybe you cannot extend. Often you cannot extend to an isometry, but you can find an isometry which is epsilon close, yeah? I mean, from this to this. This is what is approximate homogeneity. And I'm still looking for new examples of such spaces. Perhaps it could be tough, but in any case, yeah. So, but being generic in terms of the game does not require formally homogeneity, approximate homogeneity. There's no reason. There's something like weak amalgamation property or weak homogeneity, which maybe I will not talk about it because of time. Again, we are lacking examples. So there is this general problem. The problem is hopeless, I must say. But instead of classifying, find new examples. Okay, that would be more reasonable. Yeah. The game. Yeah. So, this is very easy. The two players are playing with arbitrary finite dimensional spaces. Arbitrary. So. No, they don't know about the Courant space, let's say. So the first player starts with an arbitrary finite dimensional space. The second player is adding several more dimensions, extending the norm. It would be E1, and so on, yeah? And we are building a chain, right? Chain. So and all these inclusions are isometric. So you have the union is a normed space, and you have the completion. Yeah, I can go to the slide before. It's the only thing is that all these inclusions are isometric. Yeah, so we are always extending the norm. So no functionals are involved, no dual spaces are needed. You just need basic information what a norm is, and you need to know that once you have a normed space with, say, dimension 13, you want to add another 5 dimensions, you can always extend this norm. Yeah? There are many possibilities. And it's very easy to explain even to students who do not know functional analysis except the very basic notions. Yeah? And it turns out that indeed the Courant space is, I mean, the second player has a winning strategy for obtaining the Courant space. It should not be so surprising. I mean, the strategy is more or less like, I hope I will finish on time, but strategy is more or less like, okay, if starts with some arbitrary finite dimensional space, we need to know one thing, that the Courant space actually contains everything. Well, start with E to be the trivial space, and F is E0, yes? Then E0 is inside. So the second player can find a copy of E0. And he should respond with something like E1, which is already inside. Then the game really starts. If extends it to some E2, which is outside, the second player needs to find a copy of it which is like very close, yeah? 1/2 close maybe to this one, to E1. And he should respond with something which is big enough. And so on. But these epsilons, I said 1/2, so next step would be 1/4, 1/8, etc. So in the end we will get a sequence of embeddings which converges. So the union will have an embedding into the Courant space, and if the second player was careful enough, the image is dense. He can be careful enough to make it dense, yeah? Just enumerating some countable dense, linearly dense set. And therefore, extending to the completion, you get an isometric isomorphism. So the main point is that it should be onto, not just into. Yeah? So that's how it works. Now, okay, you know, when I prepare a presentation, which I don't like so much, I prefer blackboard or whiteboard, but I'm always stressed that I do not have enough of these things. Yeah? But when the time is running, then it's typically the opposite. Okay, in any case, now, there are two notions of generic operators in the spirit of this game. Okay, now this was supposed to be the first slide, really, yeah, because I fixed this universe. Now, so our main category consists of operators of norm at most 1. So I will make a shortcut that operator is like this. Now, there is something which is, of course, not my invention. This is well known from the very beginning of category theory, that category theory is so flexible that you can create from one category, you create another, yet another, etc. Yeah? And now, so this one is that the objects are not Banach spaces, but these are just operators between Banach spaces, okay? And arrows are, I should have used colors here. Arrows are those horizontal pairs of embeddings. It makes perfect sense. I think people call it comma category or slice, I don't remember exactly. And we can again play this game. Because you see, when we are playing, instead of a single chain or sequence of embeddings, we obtain 2 parallel sequences, right? And with operators between them. So there is a limit or co-limit formally. An operator from the completion of this top one and completion of the bottom one. Okay, and this operator would be called I call it K generic because everything is based on K, yeah, on this class, if there is a winning strategy. And, apparently, if you take all finite dimensional spaces. It does exist, and it is an old result already, also of Joanna and myself. Exactly, okay, you cannot find this result in this paper, actually. It's never written. But we have obtained a Freise limit, indeed. There's this category from the previous slide where K is all finite dimensional spaces, all embeddings, is a Freise category, whatever it means. I mean, amalgamation property, etc. I will mention actually what's behind here. And this operator is like the most complicated operator on the Gurari space, and it is approximately homogeneous in a similar way like the Gurari space itself. You give me its finite dimensional part, another finite dimensional part. If you can move this to the other, you can almost extend, making a small error. But let's forget about details. Now, another possibility of being generic, like a parametrized variant. Maybe this is a slice category. I'm not sure about the names. So we are fixing a space, and now our objects are operators going into this one. Okay? So the domain is finite dimensional, maybe from a concrete category, maybe all finite dimensional spaces, maybe not. And we are, and an arrow is simply moving this to this. So it is like this E is extending, yeah? G is an extension of F. But always, this is a parameter. This is fixed. And, okay, we can say that some operator is KW generic if the second player can win for this operator. Again, up to isometry, of course, yeah? Up to linear isometry. Okay, this seems to be a little bit technical, perhaps, but it is actually useful. And the main point is that, yeah, so I'm mentioning another old work together with Félix, who is here, and Joanna, where the operator from the previous slide is actually generic in the sense of this category. So you fix G as a codomain, the Gurari space, and you play with finite dimensional spaces and operators into G, you actually get the same one. I mentioned this, okay, this 2014 was the year of publication of the paper with Félix and Joanna, and it was actually about quasi-Banach spaces, but P Banach spaces, where P is less than or equal to 1, and when P is 1, it's about Banach spaces. So, and we use this particular category, and in 2020, I wrote some short note with Joanna showing that both operators are the same. She also has a paper with Taras Banach, more recent one, showing that isometric copies of this operator really form a G delta set. Not only residual, it's really G delta. And it's quite technical. I don't understand this proof, I must say. Okay, so that's about this operator. So now what is behind why all these constructions are possible? The main point is the most complicated concept I'm using from category theory, this push out. And this purely category theoretic thing. No epsilons here, nothing like that. Everything is commutative. So this simply, okay, I think it was something like amalgamation property has been mentioned already, right? Amalgamation means, and I want to stress this thing because there are again some problems. I'm repeating this diagram. amalgamation means you have given two embeddings, maybe from your special category, maybe the category of all finite dimensional spaces. It's about finite dimensional, actually, what is important. Amalgamation means that you can close this diagram, right? By using embeddings again. Push out is much stronger. Okay, if you actually have a category with embeddings, where the arrows are embeddings, then push-outs almost never exist. But if you allow all homomorphisms, here this means all operators of norm at most 1, then there is this special amalgamation which has this property. No matter how you try to amalgamate in a different way by using arbitrary operators, there's a unique U closing this diagram. So in the category of sets, this would be, you have two sets with some intersection, you are not identifying anything and not adding anything extra. In graph theory, graphs have been mentioned by Jordi, so similar thing, but not, you are not supposed to add any new edge. And that works, yeah. And in Banach spaces, I use this symbol O plus with W, because this is indeed something like the L1 sum. This W is x plus y with L1 sum divided by something which I could call delta Z. You have to identify points with these two embeddings. So this is like a diagonal, all pairs Z, comma, minus Z. Yeah, this is what works. This is quite standard basic linear algebra. And then, okay, the only thing is to check that this F prime, G prime, there are these canonical mappings, that there are really isometric embeddings, that the norm doesn't change. That's the fact. Aha, and I feel like I should draw another picture, so I have to zoom it out, and maybe one thing which I forgot to mention. Once you are trying to build something like Fraser limits, something which is homogeneous or approximately homogeneous and universal, the key thing is having some sort of amalgamation property. Okay, two embeddings can be closed by embeddings, maybe with epsilon error, but that is enough. Okay, in practice, there are no errors. Now, the similar thing applies to operators. Now, we have, trying to draw a nice picture. We have something like that, and then another thing like that. But there are also operators between them, yeah? So there is an operator going this way, okay, maybe this restriction to this is not needed to write, yeah? But okay, let's draw it somehow. Now, we want to amalgamate this. So what we are looking for? We are looking for something like that and something like that. And an operator that completes this diagram. This is problem, yeah? This is a potential problem. So for Hilbert spaces, I don't know how to do it. Probably doesn't work. Haven't heard of really generic operators on the Hilbert space in isometric sense. Isomorphic, yes, but not isometric. But look, if this is a push out, then here you can do any amalgamation, but let's say that also the push out. Then this is this unique U, because you amalgamate from here to here, yeah, everything works. So you have a unique operator closing this diagram. So push outs actually tell you that everything works. And similarly for the parametrized category. If the parametrized category, the problem is that you have this thing, yeah? Finite dimensional space and operators into this fixed W. You still have push outs will give you amalgamation, because if you have something like that, you can make the push out, and oh, the time is really running. So you have this thing, and from the property of the push out, you have the unique extension of both. Everything works. The only thing is that when you go to, okay, if Fraser theory tells you that under this assumption, like having amalgamations plus a little bit more, you build a sequence whose co-limit is this universal homogeneous or approximately homogeneous one. If W is arbitrary, we do not know what is the domain of this operator. But if W is a Lindenstrauss space, for instance, we know that the domain is Gurari. So if W is Gurari, then the domain is Gurari. And when a bit better analysis shows that this operator into Gurari is the same as when playing with finite dimensional operators. So that is how it works. Now I have to go to the main result because my time is almost over. Yeah, I have like 5 minutes or 10 minutes. Okay, maybe 9 actually. Okay, so I must say that yeah, I have several slides on a different topic. Well, maybe I can go through this quickly. So this theorem, I'm cheating a little bit here. Maybe a little bit technical assumptions are also needed. But for example, think of this as a category of where there are countably many possibilities. Yes, finite dimensional LP, L1 maybe, etc. And that it's closed under push-outs. Then there is a generic operator in this category. And so the category K may be a little bit trivial, and you will see an example, but the operator is non-trivial. The power of freedom is part of the title of my preprint, which is on another topic, but I wanted to show now some motivation why I'm going to talk about L1, little L1. Let's go through this quickly. So everybody thinks that little L1 is a Banach space, but it's actually a functor. It is left adjoint to the forgetful functor, which assigns the unit ball. Okay, and it's actually very easy. I think it goes back to Rilke in the 60s, who first observed this and wrote it somewhere. Now it is like classical, well-known. It's a really easy exercise to check that these properties work. It's like the free group. Yeah? The L1 norm is, in some sense, the simplest or the best, yeah? The most economical. So there are these things. But because of time, I would go through this quickly. So there was a result by Dargy-Materon and then extended by Balcerzak and Kania about some kind of, maybe not generic, but good operator. Yeah? It is universal in the sense of liftings. Yeah? That every operator can be lifted, this one. I later extended it to actions of monoids, using really this freedom. Yeah? It's like L1 is a free Banach space. And what it is happening is that this operator of Dargy and Materon, they made it too complicated anyway, but any operator of this sort is not unique, but whatever you try, its isometric copies would make a small set, negligible in fact. And so Dargy at some conference was asking whether there is something like residual, yeah, or anything generic. And we have a partial answer. Partial because, being generic, the satisfactory way would be that its isometric copies are residual in the strong operator topology, yeah? Pointwise convergence everywhere. We would get pointwise convergence on a dense subspace. I mean, the union of all finite dimensional L1s. And this is an application of this, say, main result, because we are taking finite dimensional L1 spaces and very simple embeddings, those that preserve the basis. So something very disappointing, but we allow arbitrary operators, okay? And the push-outs do the job, that there is amalgamation, etc., and there is some nice operator which looks to be kind of complicated. It has nothing to do with the basis. It's basic vectors can go wherever to the unit ball. We know that it is a projection, actually. It has some universality properties, but I'm not going to mention because of time. And yeah, it works this way. And the very recent observation, which we still need to check, is that we can generalize it to obtain new Banach spaces. What is this L1? The unit ball of L1 has the property that extreme points are of distance 2. And it's finite dimensional polyhedral. We can change 2 by some r greater than 0 and take polyhedral spaces, and embeddings should preserve extreme points. And extreme points are of distance r at least. And it seems that a similar result works, and there should be some kind of hierarchy of Banach spaces that starting with L1, the smallest, and ending with the Gurari, where r is 0, no restrictions, you really get the Gurari space again. Okay, let me finish maybe by coming back to push out. So I promised to show this slide, this result of my former PhD student, Claudia Viscardi. Unfortunately, still unpublished, but it's my fault. I was thinking about putting this as a part of a bigger paper. In any case, this is a nice result saying that if we are playing with push-outs and allowing subspaces, you end up with the Gurari space. There's no way to obtain new Banach spaces. Only when you restrict the class of embeddings to some very special embeddings, then there is a chance. Otherwise, no way. And what is an annoying problem? There's no other amalgamation that would work for some, say, let's say, uniformly rotant spaces or things like that. Nothing. I know nothing about it. For instance, we have uniformly rotant spaces with this modulus of convexity, or how you call it. Do they have amalgamations or approximate amalgamations? Still don't know. I think, yeah, here it is full subcategory. So, yeah, for instance, this is this question, what I wanted to say. And then, yeah, which separable spaces have a generic operator, you know, in a reasonable operator topology, yeah, or in this sense of this game? Again, not clear. Finite dimensional spaces closed under push-outs, but here it would be that you are restricting maybe embeddings, yeah, to certain class. Okay, maybe the last problem is not so interesting. The first question is, in my opinion, quite good, yeah. And the last thing is that whenever you give me a class with amalgamation, there is also this to be checked. Yeah. You can correct epsilon isometries, but there is at least amalgamation, new ways of amalgamating spaces, and then operators, of course. Okay, so thank you. That's all.
Do we have questions?
Thank you, Wisha, for your talk. So you were mentioning at some point Hilbert space that you don't know, or that there is a generic operator? Or?
Yeah, but I personally do not know, but I think that people in operator theory would know that either there is one or there are many. I think that if you allow isomorphisms, then Then there are many probably. I saw something like that, but I don't remember.
Oh,
Yeah.
but in the isometric, if you just allow isometry, do you think there is not? Or
You would take operators of norm 1, and you take an operator of norm 1 and all its isometric copies, yeah? Whether there is a residual one. I don't know.
Okay.
But I'm not an expert in this. Operator theory is a pretty wide branch of functional analysis, so I would guess that some people know whether there is one or there is no.
Okay.
And I have some colleagues whom I can ask. Yeah, so, yeah.
Thank you.
Well, so, and you don't know also for the LPs in general?
I don't know. I don't know, because amalgamation is not a push-out, yeah? It's something...
But there is amalgamation.
There is, yeah.
So, and it is not that, it's a little more complicated.
Yeah, but it is something worth trying, maybe, yeah. Maybe the amalgamation is so good that you can extend to operators.
And
Who
you
knows?
have this correction, you have all these things are in
These
there.
things work, yeah.
Yes, so, and then there is this other thing, Martino Lupini maybe has some universal operator for, not a universal, Freisel limit for L2, maybe. I don't remember exactly, but he was doing things of this kind.
Yeah, I will check it, thank you.
Further questions? Just a comment. All Banach spaces have functors. We'll be back at 12:30. Next time the speaker again. Good. It's an immense pleasure to introduce to you to Professor Mastilo, that we finally have here at Badajoz after several tries. He will speak about domination and factorization theorems for multilinear and Lipschitz operators.
Thank you very much. So at first I would like to say thanks to organizers for the kind invitation, and especially to Professor Castillo. So it's nice to be here and touch this beautiful area of Spain. I would like to present some results related with this topic. So, you know, I work in interpolation theory, so interpolation method allow to produce a large class of beautiful Banach spaces and define relation between them and operators between them. So the construction are abstract because in general there are quotient of special spaces of operators between Banach spaces, and there are many universal construction. One of them is real and complex method, and abstract minimal and maximal constructions which produce this classical spaces very well known in literature. So this problem in interpolation is related with the linear case, but for the large class of spaces, whenever we know results for linear, we can prove results also for non-linear case, highly non-linear, including Lipschitz. But I will be not talking about this. So in applications in this theory of operators, this is very important to know about the spectral analysis and relation with the S numbers in the sense of pitch. So in this kind of problems, it appears, as we can see in many beautiful monographs, that factorization theorems play a very important role. So let me, okay, this is the schedule of my talk, so I will give some introduction, preliminaries, mention about some known results, about factorization, and then we enter to summability of Lipschitz maps, and then we discussed a little bit about Pizier famous theorem, and then later I will discuss about Nikishin theorem. So in order to be clear what we So we have a measure space, sigma finite measures, complete measure space. So this is the space of all measurable classes, and we consider the topology on this space a natural one, converges with respect to measure. And of course, in some problems, even in the study of maximal Hardy operator on homogeneous metric spaces, people talk about the quasi-metric, like we are saying about quasi-Banach spaces. So this is the general situation. So we have a function on a product, the quasi-metrics in this sense, okay? And so we have this triangle inequality with constant k, which is from 0, 1, when 1, this is a metric. And whenever X is a linear space and we have homogeneity and at this sense, then this functional, that on the second coordinate we put 0 from this space, this is gives a quasi-norm. So a quasi-Banach lattice, which is a linear subspace of the space L0, is called a quasi-Banach lattice whenever it has an ideal property in this sense. Yeah? If modulus f is bigger or equal almost everywhere from G, and f is in the space, then G is also, and then we have monotone property for this quasi-norm. Okay, so it seems does not work. Mm-hmm. So there is a nice observation of Gustafsson that we can always introduce a metric on a quasi-metric. So this is a variant extension of Aoki-Rolevich theorem, which says that with this, P, with P between 1/2 log with the base 2k of 2, we have the following, oh, strange. I hate this, so maybe I will really use this arrow. So we have this estimation. So we have a quasi-Banach lattice, and P between 1 and 2, then we have a P convexification. Professor Lancier gave the definition for the Banach sequence space with unconditional basis. So this is just a general variant on a given measure space. So this is space of all functions that the modulus to power P belongs to our quasi-Banach lattice. So, and this gives you a quasi-norm in general. Whenever this is Banach lattice, P is bigger than 1, then this is a new Banach lattice. So if the dual separates points, X is called P admissible. So a quasi-Banach lattice X is said to be P convex whenever there is a universal constant for which we have this vector valued inequality. So this is just LP norm in the strong sense, and this is in this lattice says P norm pointwise, and we take this measurable function, and this must be true for ON with universal constant C. And this C, the best one, is called the P convexity constant for our Banach or quasi-Banach lattice. So a simple observation, if P is P convex, even only if with constant 1, this I mean, in general, then this 1 over P convexification is P normable. In the case of quasi-Banach spaces, our space may have a trivial dual. So the Maquis semi-norm on a quasi-norm space, this is a Minkowski functional, so the convex half of the unit ball. So this gives a semi-norm. So if the dual space separates points, we have this is a norm, and the completion is called a Banach envelope. Yeah, So what you see, the Maquis norm, so this is the strongest topology will give the same topological dual. Yeah? So I mean, there is a general notion, if you have a topological linear metrizable space, the Maquis topology is the strongest locally convex topology which gives the same topological dual. And the base of neighborhoods for this topology is formed by convex hull of the neighborhoods of the original topology. So then, in this case, this norm produced the same topological dual as the original one. So Carlton in 1978 proved a beautiful result that if X is not locally convex quasi-Banach space with separated dual, then Banach envelope maybe not always is not good. I mean, it contains always uniformly L1n. Yeah, so this means that if you take any natural number and you take epsilon, we always find finite dimensional space in the dimension n, and isomorphical embedding that the Banach distance is just less or equal 1 plus epsilon with this given epsilon. And this for On is true with On. So this means it contains uniformly L1n. So surely this Banach envelope has a trivial type, because this can be described in these terms also. So a quasi-Banach lattice is said to be strongly P-admissible whenever P-convexification dual separates points of XP. Okay, so now just the definition which is well known in literature. So this is the extension of the definition of pitch. So if we have P and Q between 1 and infinity, P is less than or equal Q, Mityagin and Pełczyński in their paper in Studia, they gave the definition to be QP summing for bounded linear operator whenever there is a universal constant that for any finite set of elements in our domain, we have the following estimation. So on the right hand, this is LP norm, and we run with the supremum over O functionals in the unit bow of our X, and this is LQ norm for the values in the space Y. So the best constant here is denoted by this whenever P is equal Q. So this is exactly P summing operator. So maybe few words. I mean, this class was introduced because of application in the local theory of Banach spaces and theory of operators, and especially whenever X is equal Y and P is equal to this class of operators has a deep application in the eigenvalues of distributions. So I mean, I study with, I mean, instead you see here LQ and LP, you may take the Banach sequence lattices on the set of natural number, and there is an extension. So this kind of extension I use in some papers on interpolation of operators, which gives you, give you to show that the range space can be smaller one than by any interpolation functor. So this is related with summability property. So pitch proved a deep, beautiful result which has many deep applications. It gives characterization of P summing operators. So this is the part called the domination, pitch domination theorem. So T is P summing even only if there is a probability Worrell measure on the dual unit bow with weak star topology, for which we have this estimation with universal constant. So all possible, if you take all possible C, this exactly gives this the best constant here, but this is not essential. So the point is that whenever we have this kind of estimation and we have some information between spaces of our operator, then we can do a game with this beautiful inequality, and we get just non-trivial information then in general. So from beautiful Grothendieck theorem that any operator from N1 to Hilbert space is one summing, so absolutely summing, shortly saying, follows the following result, also proved by Grothendieck. So whenever we have two compact Hausdorff spaces and we have a bilinear form on the product of CK spaces, then the probability measure on K1 and K2 respectively, for which, for this bilinear form, we have the following estimation via Hilbert norm, so extension. So CKs are of continuousness, of course, embedded in L2, but this allows to show more. And so the best constant exactly in this inequality is called this famous Grothendieck constant, which is still unknown for now. So people now, they use this local version of Grothendieck, and whenever we know the best constant, then this is used in computer science. So there are many results about this. So now, let me mention about, to give a light what I would like to talk about. So Pizier proved the following result: whenever P is less than Q, yeah, bigger than 1, less than infinity, and we have an operator from CKs to Banach space, then the following three conditions are equivalent. So this is Q1 summing with Q equal 1. There is a probability Borel measure on our compact K such that T admits factorization. So this is the inclusion map from CK to the Lorentz space. Here there is a definition. And of course, if this is identity, so you see, we see what is S in fact. And this is equivalent that instead of P equal 1, you can also put P bigger than 1. So those three conditions are equivalent. So this is a Lorentz space, which we may define on any measure space. So this is in this case. So this is the space of all measurable functions for which the distribution to power 1 over Q belongs to L1 on R plus. So in terms of rearrangement of F, we can, so rearrangement of this is generalized inverse of this function, can be written this way. So I mean, in recent years, people try to extend the results in the linear case to bilinear or multilinear case. In general, there are results true for bilinear, but not for the multilinear with n bigger than 2, and extend to non-linear case, then to Lipschitz, and to non-commutative case. And of course, for this we need some kind of machinery, and both results then have applications in multilinear problems. Also, there is a theory of S numbers in the sense of pitch and so on. So the results I am talking about here are joint result with Enrique Sanchez Perez from Valencia University. So the first result says the following: whenever we have P and Q like between 0 and infinity, and 1 over S is this combination, classical 1 over P plus 1 over Q, and we have two quasi-Banach lattices, and X is strongly 1 over P admissible, Y is strongly 1 Q admissible, and if we have a constant, positive constant, then the following statement about bilinear operator to quasi-Banach lattice are equivalent. For any finite sets in respectively in X and Y, we have this vector evaluate inequality, where here is a Banach, I mean Makin norm, because we assume this is Makin norm in this 1 over P convexification. So this vector evaluate inequality is equivalent to the following inequality using functionals. So usually, I mean, in many cases, whenever we have a class of operators and we are able to show that this class satisfies some vector valued inequality, then in general to verify those inequalities is difficult, but under some conditions, is it possible to show that we can simplify the description, but of course we need some machinery, so some separation of key-fan theorems in many theorems. Key-fan theorems is used to prove this general kinds of results. So whenever X is P convex, Y is Q convex with constant 1, then of course there are Banach spaces, and we see this completion is exactly X1 over P, and so on. So we get that the situation with in the Banach case. So what about the next result? So in general, the description in terms of you know, some inequalities which involve measure on some compact sets is not possible. So, but for the weaker class, like positive, is it possible? So this is one of the type of results. So if we have a P and Q, P between 1 and pk between 1 and infinity, and for n-tuples, this classical P convexity inequality, and we have a P concave Banach lattice, so in a sense dual notion for to be P convex, an n-linear positive operator from this Banach spaces to this E, which is, yeah, that there are positive functionals in the unit ball of this 1 over P convexification, for which we have this inequality. You see, this inequality is the opposite one. So here is the strong LP norm, and this is a lattice LP norm, our functions in E. So in the case whenever E is equal LP, then we have that this is P concave and P convex, and in fact this is only in general the case. So we were interested, what about the variants of Pizier result? Pizier beautiful results found many deep applications in theory of operators for which the domain is a Banach lattice, or range is a lattice. So there is a trick that we can lift the summability with composition of positive operator from CK space to this given Banach lattice, which is a range of our operator which goes from this Banach lattice to Banach space. So this is some variants, so I am not able to present with variant which involves the Fremlon generalized Fremlin tensor products. But so this is the following variant. So this is a definition to be factorable QP summing. So this means, so we have a multilinear operator between Banach spaces. So this is exactly definitions. So for n tuples of matrices correspondingly in our spaces, we have the following vector valued, looks really complicated, estimation. So this means to be, so you see we put for all, we do summation with respect to the second coordinates, yeah? And then next one, take the norms Q, and LQ norm, vector valued LQ norm, and we want to have estimation by the expression which involves functionals. So, for the results, which we show for a moment, it will appear the following operator, which will be in the factorization. So then this is exactly, I mean, the product. So multiplication, pointwise multiplication. So which is denoted by C dot, and which is of course well defined on on a measurable spaces. But we are interested in the case of CK spaces. So this is, so for simplicity, let me present the bilinear version only. So, as I told you, Pizier has a linear operator from 3K to Banach space, and there is a description whenever this operator is P1 summing. This is exactly via factorization through the Lorentz space, which involves the parameter of summability. So T is factorable QP summing, and for each positive integer and blah, blah, blah. So this is exactly the repetition, modified repetition of the definition. We have this inequality. And the essential point is exactly equivalence of those three. So this T has a factorization through the Lorentz space, which involves the first Q, which is in the domain in this inequality, and here is exactly this dot operation. So this is linear and multilinear. Yeah? So if we fixed coordinate, we have a linear, but multilinear is a not linear. This multilinears are Lipschitz also. So many problems in recent time, people apply, I mean, some kind, a new age again come, because Lindenstraut, Safiri, Schechtman in 70s, they proved many beautiful results about this Lipschitz embedding of metric spaces to finite dimensional Banach spaces. So, and those results now have many applications in computer science. So in 2009, Farmer and Johnson, in their Proceedings Mathematical Society paper, introduced concept of the Lipschitz p-summing operators between metric spaces. And they proved the pitch domination theorem and factorization also. I don't have a time, but I mean, there is its domination has an equivalent formulation via factorization through the subspace of LP. When P is equal 1, then exactly there is a factorization through the Hilbert space from CK. So, okay, so you see, and they prove, so the differentiation will come, and they proved, and they show some nice application, and in this paper they mention about Bourgain result from 1985, in which he studied distortion of Lipschitz embedding of metric spaces to Hilbert spaces, and in fact, in these papers there is an idea of the summability. So they are saying in this paper, so the precise definition, we have two metric spaces, and we have a map between metric spaces, and which is Lipschitz in classical sense. And so, to localize the problem, so we fixed a point in a metric space denoted by 0, but 0 is maybe this is maybe not a linear space, but people just write this way. So let me go follow. And so this is the space of all Lipschitz functions for which the value at this fixed point is 0. And so this is a Banach space with the following norm. So now, so here there is a definition with P and Q. So we have a subset of the unit ball of Lipschitz function on a metric space, and we consider this with and this is a compact with respect to the pointwise topology. And we have a Lipschitz map, and we said that this is PQV summing, yeah? Whenever there is a constant, that for each n and for any choice of elements, we have this inequality. So okay, so maybe later on. So whenever V is O unit ball, then this is called QP summing. And this is exactly whenever P is equal Q, this is this definition introduced by Former and Johnson. And they prove that so the best constant is just called QP summing norm. And they prove that in the linear case, the Lipschitz definition and linear definition gives the same norms for the linear operator between Banach spaces. Okay? So this is their result. So let me only write it in the form of domination, because there is also third one condition equivalent, which is the variant of Lipschitz factorization. So Lipschitz P summing norm is less or equal C. This is equivalent that there is a probability measure on this compact unit ball of our Lipschitz space, yeah, for which we have the following estimation. Yeah. So in their paper, then they mention about the paper of Bourgain that the proof he has gives Lipschitz N1 norm of identity on any endpoint metric space. There is a universal constant for which we have this estimation. And surprisingly, this inequality found in many deep applications, even in local theory of Banach spaces. You can see in some papers. So okay, this is trivial. So maybe I will skip how to build operators which are on this type. Okay, if we know one example, we do composition, and we can have an operator in this class, and also we have estimation of this QP summing norm. So you see, whenever X is a Banach space, maybe I should come back. So whenever N is a Banach space, and this set U is the space of all linear functionals, yeah, from the unit ball of linear functions, there are special Lipschitz functions. So then, instead of this, writing L, we will use star here. For Lipschitz summing with respect to this W set of functionals. Okay. So later on we will see the more general definition of cotype. So whenever the domain is CK space, and this is a W is exactly the unit ball of all functionals on CK, so it's easy to see that taking the supremum over all functions in the unit ball, then this expression is exactly this expression, pointwise expression of this difference in L infinity norm in CK. So roughly speaking, this means in the sense of extension of the notion QP concave in this in the lattice. This is exactly what we are saying here. So this is exactly the definition to be Lipschitz QP concave. So let me come back again to PZS theorem from this. This is a beautiful paper in Mathematischen Annalen from this year. He has also non-commutative version. So a linear operator from CK to Y is Q1 summing even only if we have I'm writing only this domination from this previous one statement. And then, so this was natural. What about the class of Lipschitz operators for which we are able to see that we have a variant of each, and the situation is really in general complicated. So whenever if you do analysis of PZS theorem, this is equivalent to the following statements. to be Q1. Okay, because of linearity, you can reduce the problem that the norm is 1. So there is a probability measure for which we have this estimation with universal constant, which of course, but which depends on Q, because Q is fixed. And then this estimation is on the unit sphere of Ck. And there exists a probability measure on K for which we have the following estimation, Lipschitz of time estimation. And so here's, I mean, there is a comments how the proofs go. Of course, the non-trivial case is the implication 1 and 2. Of course, this example shows that in general we cannot expect a variant of Pizier result. So simply we used classical fact that if you have a Banach lattice, so you put the value on x is x whenever the element is unit bow. Whenever this is not in the unit bow, out of the unit bow, x over the norm of x. And this is a Lipschitz with constant 2. Yeah? And then if space is infinite dimensional, then Benjamin-Stanford proved that there is a retraction from x to the unit sphere, and then we composition with this map. And take any operator from Ck to x, which is Q1 summing, but this one will not be satisfied this inequality. So no chance to get this measure which will give the estimation domination of this type, as in the linear case. Okay, so, I mean, so here there are some class of Lipschitz function with some property to subadditive, so maybe I will not discuss very carefully, blah, 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 blah. And monotone, I mean, there are examples, general examples. So for this class of Lipschitz operators, so this is subhomogeneous in this sense. It appears in some papers of Naor, such kind of Lipschitz operators they study for the embedding. And again there is a problem, I see. Okay, no. And also we have a notion for the metric sublinear in this case. Yeah. So, okay. So here in fact, there is a general lemma which shows how these notions we introduce is related with some general property of the metric we can introduce in CK. In fact, I don't like to bother you with this, but the point is that under some conditions, yeah, we have the following results. So, if we have a metric space and we have a Lipschitz subhomogeneous QP concave map, let's say with constant 1, blah blah, yeah, and this subset also we require to be the compact with respect to pointwise topology, and if this attains the CK metric attaining and set of subadditive and monotone, then there exists Borel measure for which we have this kind of domination. So this is I mean, this is a variant. This is a Lipschitz variant for this class of operators of Pizier domination. Okay, under the different conditions also we get this one, but I don't like to talk now about this. So let me shift to the Nikishin theorem. So Nikishin proved in 1970 the following result, and this was related with Quapian question, which is unsolved for now. So if we have a Banach space which we can embed isomorphically in the linear sense to L0, originally to the space of measurable function on interval 0, 1 with a Lebesgue measure. So if this is true, that this space can be embedded to L1 on interval 0, 1. And this is unsolved for now. So Nikishin, so I will present results. So we show an extension of Nikishin theorem. So for this we need the definition. So we consider of functions which are increasing, continuous, and bounded at 0, 0. And whenever this function is convex, it is called an Orlich function. Yeah? And for this type of function, we define the generalized Marcinkiewicz space. So this is the distribution of our function. Yeah? So we compose with our phi and multiply by lambda, and we want that the supremum is finite. Yeah? So you see, whenever you take phi of t 1 over p, then you will get a classical LP weak Marcinkiewicz space. So any LP is continuously embedded in LP infinity. So whenever p is between 1 and 0, this is a quasi-Banach. Whenever p is bigger than 1, then there is an equivalent norm on which, a quasi-norm, a norm which gives that this is a Banach space. So, following the definition in Wojtaszczyk book, so given a metric space, a measure, so the definition was for Banach or P Banach. I mean, Carlton had some result for P Banach. And then we have a map from X to metric space to the space of measurable functions. And we say that it factors strongly through Marcinkiewicz, L phi infinity, with this given function in our class capital phi, for which we have this estimation. So if we read this inequality in terms of the quasi-norm, this looks like this. Yes, because if we multiply, take supremum, and then we have this estimation. Okay, we could put constant on the right hand, but this is not essential now. So this is equivalent, you see, this is equivalent that we have for this our operator the following factorization through Marcinkiewicz space, and here is a multiplication operator. So, probably, I mean, everyone knows of the definition of Orlich space. We have a function in phi. It may be not convex. So we define the following function, the space of all function for which this functional is finite for some lambda. So this is an F space with the following F norm, which is complete. We consider such phi for which this functional gives a quasi-norm. So because this is for any measure space, but the measure is not atomic, this is in fact equivalent with this condition. So then this gives then a quasi-Banach lattice. And this constant in the triangle inequality exactly will be this constant for this function. So, if the measure space is discrete, we get an Orlich sequence space, so simply integral is a series, and so we see the expression. So if we do localization, do projection on n coordinates, so this is finite dimensional Orlich space. So simply Rn is equipped with the following norm or quasi-norm. It depends on phi. So later on we will use the following function. So whenever functions satisfy delta 2 condition, so this means that with constant 2 we have, this supremum is then finite we want to have. So this generates a submultiplicative function on positive line whenever phi satisfy delta 2 condition. So, and whenever this approaches to 0, this means by the definition that the function is a capital phi 0. So this is related with the lower index of Matuszewska-Orridge, or they are saying also Boyd is non-trivial. But I mean, to say about index, we need definition, but no sense to bother you. Okay, again. Okay, so this is this version of Nikishin for the Lipschitz. So XD is a quasi-metric space. T is a mapping. So we assume that our measure space is a probability space. Function phi is in phi 0. Then we have those three conditions are equivalent. Without this assumption, there are some implication, but I would like to see equivalence. So T is strongly factors through Marcinkiewicz, which is an inverse to this one. There is a function C on R plus to R plus, which approaches to 0 whenever lambda approaches to infinity, that for all positive scalars, we have the following estimation for the distribution of maximal function generated by this. And lambda, of course, you see, we count the norm of this sequence in n-dimensional Orridge space. And for applications, this one is very essential. For every epsilon, there is a constant, depending on this epsilon, and a subset, measurable subset, that the difference is less than epsilon, for which, if we multiply by characteristic function of this set and we calculate the quasi-norm in our Marcinkiewicz space, that it has an estimation via the metric. So roughly speaking, restriction gives that you have that this map is Lipschitz in this restriction to this Marcinkiewicz space. So this was for general Lipschitz situation on even quasi-metric space. But using this Gustafsson result, really we can always shift to the metric case. But in the case of Banach spaces, so applications which appears in literature are for the sublinear operators. Yeah. So sublinear means as it takes value in L0. Yes, is almost everywhere and homogeneous. Yeah? So then we have a corollary. Then if we have an operator which is a sublinear in this sense from our quasi-Banach space, and phi is in phi 0, then the following conditions, this modulus is strongly factors through Marcinkiewicz generated by inverse of this function, blah blah. There is a function for which we have this estimation for the maximal operator for the distribution. And the second one, yes, so for application. So now we would like to see applications. So Nikishin gave applications okay, so here there is a definition of this is an extension, the extension of the concept of to be Rademacher and on type or cotype in the LP setting. So the quasi-Banach X is of cotype phi, yeah? Whenever this function is our class, you remember, for which we have the following estimation. So this is the sequence of Rademacher functions. So the norm in X, and we integrate with respect to measure space, and then we need to, that this is estimated by the norm of sequence in our origin sequence space. So this will mean that, I mean, gamma is a universal constant. The smallest one is type phi constant for X. So the proposition says that whenever there is a quasi-Banach space of type phi, and S is a sublinear operator, which is continuous at 0, then there exists a function from C plus C plus to C plus, which approaches to 0 whenever lambda approaches to infinity, for which we have this estimation of the distribution of the maximal function via the constant of type. Such kind of estimation in general appears for application in stochastic processes, and so this is very useful in general. So for example, you see we can take an operator which is sublinear and maximal Carleson operator, which is maximum on the circle of the partial sum of the Fourier series. Yeah. And Nikishin exactly gave application of his result to the trigonometrical series also. So this estimation then is true whenever we know that the sequence is in the unit ball of this origin space. Okay, so this is the conclusion from these general results. So whenever X is a quasi-Banach of type P, so this means that origin phi of t is equal to power P, so this is exactly the classical case, and P is between 0 and 2, and only this one must be from the by the property of the Rademacher functions. Then, and we have an operator which is continuous linear. This variant of the Nikishin was proved by Carlton in his deep paper in transaction. He has many applications of this result, and so he studied operators to the space LP, P between 0 and 1, so quasi-Banach space, the space with the trivial dual, of course. And in particular, he proved the following result. Whenever t is from P to L0 continuous, and if P is between R, you take R between 2 and bigger than this given P, which is from the interval 0, 1, there is a subspace V of LP, which is isomorphic to this LR. Yeah? He used his variant of Nikishin to prove this. Okay, this would be another question. What about the Orlich case? But in the Orlich case, we know the result of Lindau-Safir of the description of the embedding of LP spaces to Orlich. This deeply depends on the indices of the function, and surely this situation will be in the quasi-Banach case. We didn't study this, but surely it will be involved. So now the question is, what about examples? How to produce examples of spaces with non-trivial Rademacher Orlich type? So if we have a given Orlich function, so convex, so we define the conjugate function in the sense of Young, the following. So it in supremum may be infinity, so whenever we assume that phi of t over t, if phi is convex, phi of t over t is non-decreasing. So then in this case, this is a finite function. So this is again an Orlich function. So take 0 at 0 and positive, and convex. So using the Kette duality, so this is the space of integral functionals. Yeah? So the Kette dual of L phi is up to equivalence with the universal constant 2, the Orlich space generated by the conjugate function. So we have the following, and in fact, if you study carefully proof for the LP that this gives, so whenever X is a K convex, in the sense of Pizier, so this means that it has a non-trivial type, and phi is a convex Young's function, x is of cotype 5, then conjugate of our Banach space is type of phi star, where phi star is the Young conjugate function for phi. So examples. So this was here mentioned many times. Banach space is uniformly convex whenever the following functional is positive for epsilon from 0, 1. We see by the definition that epsilon must be from this interval. So this is so-called the modulus of uniform convexity. So whenever this is positive, that space is called uniformly convex. And the modulus of smoothness, introduced by Lindenstrauss. And, okay, this is, I am repeating what here, so it's written precisely when to be smooth, this one. The modulus of convexity and smoothness of Banach space and the dual are related by the following formula proved by Lindenstrauss. And then you can find this in his paper, but this is in this famous book with Safiri. So this is what is known, how those functions behave. So this is only for this that whenever we know this, surely to be that the space has non-trivial Orlich type, this L phi must be continuously embedded in little Hilbert L2. So this is exactly, so this function is equivalent to convex function in natural if we extend, because the norm does not depend on how, for large T. So if we have vixification, we surely have this embedding. This is the Majorand, convex Majorand. So we have the following. And in fact, this fact is not written precisely, but the proof shows in our language, which comes from Figel and Pizier, that if X is uniformly smooth, respectively uniformly convex, Banach space, then X has a type rho of X, where this is the modulus of convexity, respectively cotype the modulus of convexity for the taking the convex Majorand of this modulus. Okay, so this is only. So using the technique for this Nikishin theorem, we were interested to this maximal inequality, and this is the variant which we believe can be applied to some problem in stochastic. So it says the following, that if you have a quasi-Banach space of type psi, which psi is in this our class, phi in this one, and we have estimation for this maximal submultiplicative function like this. So it's very easy to produce a huge class of the function of this type. And suppose we have a continuous sublinear operator, but now it takes value in our Orlich space, then we have this maximal estimation of the maximal operator via the vector valued norm of this sequence in fact, Kette-Bochner L Orlich X, for all sequences in X. So thank you very much for your attention.
Do we have questions, comments, or remarks? Okay, if not, we will meet at in this room. The session of this evening will be in this room, right? Not in front, in this room. Let's sound the speaker.
Thank you very much.